Okay, so we will have a new next talk in a moment, in a few minutes. But we would like to use this technical break and remind you the schedule. Doesn't work. Не хочет переключаться. Okay, we remind you our schedule. So we will start next lecture by Professor Vicky Bass on brand preferences. Next, we have a break. After the break, we have two talks by Alex Asacchi on methodology, EEG-based fMRI technology. Yanni, who is here, will give a talk on neural mechanisms of persuasion and healthy eating goals. I remind you that we have a second part of Zarasa's workshop on surface, on voxel-based morphometry. I actually attended yesterday. It's a nice tutorial. Feel free to join and continue the data analysis of the structural MRs. And we have a poster session. Yesterday it was a very successful, very interesting poster session. I encourage everybody to attend and give feedbacks to students, PhD students. Okay, I will use this opportunity to remind you tomorrow that we have Ksenia. Tomorrow we have also two sessions. Nina Kazanina from University of Bristol will give a presentation on neuronal implementation of language and thoughts. Anna Izmalko, who is here, will talk about the vocabulary learning studies. And after the break, we will have a presentation on metacognition. Ksenia, who is here, will give actually a very interesting workshop on regression analysis. Feel free to join. Please, tomorrow during the break, we will ask you whether you are interested in a tour in our center. With Nina, we will ask if we have some people who would like to make a look to our laboratories. At the end of the conference, we can show you our labs. Just indicate tomorrow your interest in this, okay? I would like to also remind you that we have few laboratories, not all of them are here, but we can show you TMS, infrared, near-infrared spectroscopy laboratory, EEG, eye tracking facilities, few brain stimulation labs, and so on. We'll be happy to show, and perhaps we can also provide a glass of champagne. It's all located here. We will give a short tour to our laboratory. It's located in this area of the same building. Also, we would like you to distribute some information about our master program, because at this moment, many future current bachelor students are interested in master programs. We have here a master program, English-speaking program on cognitive sciences and technologies. And we will be happy if you will share information about this master program. We're looking forward to see bachelor students from various universities. I would like to remind you that if you're an PhD from a different university, you can use this project for Russian postdocs to get a decent salary and a place to live in Moscow. And 1 or 2 years, I think, yeah, will be supported by HEC University. And also, I would like to remind you that there is a program for foreign postdocs, postdoctoral fellows. We will be happy to share this information for postdocs and also for tenures. We also would like to make an announcement about a conference.
Yes, okay. Hello, everyone. My name is Anna Izmalkova. I'm a postdoc researcher at the Institute of Cognitive Neuroscience. And I would like to invite you to our school for young researchers, PhD students, master students, bachelor students who would like to gain impression on brain mechanisms of thought and language. We're going to have a very interesting school in November on the 15th, 16th, and 17th of November. It will take place here, and one day will be at Moscow State Linguistic University. You will have an opportunity to listen to distinguished lecturers, distinguished scientists, and the main idea of the school is to promote information on how to turn your idea into a publication. So there will be some practical tips in masterclasses, in workshops, and so it will be extremely useful for those who are beginning their careers in neuroscience, in language studies, and an excellent opportunity to meet with fellow scientists from Russia and from other countries. We'll have professors from Northumbria University, from Aarhus University in Denmark. So please join and follow the news on the webpage of Institute for Cognitive Neuroscience for future schools and conferences. So keep in touch.
So this is early announcement of the school. We will put some news on the webpage of the Institute for Cognitive Neuroscience soon. But please screen our web pages. It will be an interesting English-speaking school. English-speaking school with lecturers from Britain and Denmark, Moscow, and so on. Anna, do you have a few words?
Not that I have more to add to our advertisements, but perhaps if Professor Vicky Butt is around, we can start with his lecture with my yet super quickly preface. Vicky is our long-standing collaborator from India, from Birla University of Technology. And Vicky specializes in many things, including neuromarketing, which is super interesting in the light of naturalistic stimuli and social neurobiology. And today, Vicky is going to talk about posterior contralateral negativity as an indicator of brand preferences, which is something very new to me and super exciting for the context of our school or of our conference, sorry. Vicky, can you hear us?
Yes, I can hear you.
Okay, good. Will you be comfortable with sharing your presentation?
Yeah, I'll do that. Thank you so much.
Oh, good. We can see you well. Good, great.
Okay. Can you see the screen?
Can?
Yeah, okay.
Shall we start? I think we can start in order to finish a little bit earlier or leave more time for questions because I anticipate there will be many.
Okay. Yeah, so thank you so much. I'm Vicky Watts. I'm from BITS Pilani, and currently I'm in Northumbria University. I gave a talk yesterday at Andre's lab, and so thank you so much for the kind invitation. So I'm heading the cognitive neuroscience lab at BITS Pilani, KKBL Goa campus in Goa, India. And our lab is focusing on four important areas. First one, we are working on dementia detection from conversation transcripts using deep learning. That is one approach for dementia we are working on currently. The second one is we are developing technology for AR and VR based technology for dementia care. And third one is we are using graph models to understand dementia and Alzheimer. And fourth one is, of course, on AI and consumer neuroscience, where I'll be talking about the posterior contralateral negativity and indicator of brand preference today. So most of the work we do is on deep learning and machine learning and artificial intelligence to understand Alzheimer data. And we also use AI and sentiment analysis for consumer neuroscience work as well. So mostly the graph work which we are doing is also we are replicating to understand consumer buying patterns and buying behavior. So we have vast amount of information about brain's structure and function. Like we have tons of data related to brain structure and function, but we have a very poor understanding about the exact relationship between brain structure and function. So we use graph models and we convert the neuroimaging data into graphs and networks. So simply graph is the collection of vertex and edges. So you can convert the neuroimaging data or the complex brain data into the language of simply nodes and edges. And the beauty of this conversion is that it is amenable to different kinds of mathematical analysis. Like you can construct adjacency matrix, adjacency list, cycle matrix, path matrix, and so on. And it gives you a very better understanding about the neural correlates involved in, like, in case of dementia also. And we are using the same discrete mathematical models to understand consumer buying patterns and buying behaviors. Because cognition is a very dynamic and distributed process. It involves the coordinated effort of different brain regions. So if it is linked in that way, then the graph models really helps in understanding the buying patterns and buying behavior of the consumer. So that is for dementia also we are using graph models, and for understanding consumer behavior also we are using the graph model study. So today I'm going to talk about posterior contralateral negativity and indicator for brand preference, and this work is we are doing in collaboration with industry. They funded our lab, and they are into AI and marketing. They provide analytics to their clients. So we most of the data we collected it from uh, the course 5 intelligence, and we used our analytics to understand the consumer buying patterns and buying behavior. So before going deep into this, I'd like to touch upon some basic things about the neuroscience of consumer behavior. And as you can see from this slide, that the goal of consumer neuroscience is to predict consumer buying patterns, understand neural correlates of consumer behavior, motivation, and preferences, then manipulate consumer preferences, creative evidence-based advertising, then product development cater to heightened consumer buying, and impactful product marketing. So the this is how this is the neuroscience of consumer behavior. So we have to understand and predict the consumer buying patterns, and then you can manipulate the consumer preferences also if you have the neural correlates of somebody's likes or dislikes. Or is there a buy button on the brain, or is there, like, you can find a way by which you can understand the neural correlates of likes or dislikes. Then it will help you in having a very creative and evidence-based advertising for influencing consumer buying patterns and their buying behavior. And it will, of course, provide you very impactful product marketing. So there are different approaches or techniques being used, how it works, and these are the things we use for understanding consumer behavior, buying patterns, and understanding why they like something. Is there a like button on the brain? If they dislike something, is there a dislike button on the brain? Or what are all the neural correlates? So how it works? So we have fMRI. You all know about this. It's a functional magnetic resonance imaging. It detects blood flow in the brain associated with increased neural activity. Then we have electroencephalogram. It records the electrical signals on the scalp from neurons inside the brain. Then we have eye tracking. Eye tracking, like the gaze, it detects exactly where the subjects direct their gaze. Then you have eye tracking, where it measures whether subjects' pupils are dilated. Then you have biometrics, like we have GSR we use, measures skin conductance, then heart rate and respiration. Then, of course, we also use facial coding to identify facial expressions. And what it reveals about consumers, fMRI gives you detailed emotional responses and level of engagement and recall. And for an electroencephalogram, gives you a level of engagement recall. And eye tracking gauge what grabs their attention and what confuses them, and the speed of recognition. This kind of information you get from this eye tracking gaze. And then eye tracking pupillometry, you get the level of engagement, the consumer's level of engagement, which is very important. And from biometrics, you get the level of engagement, whether their response is positive or negative. And in facial coding, it gives a general emotional response, like the subject or the consumer, they're happy, surprised, fear, and so on. And then uses, you can see the set pricing, it improves branding, that is for fMRI, and for electroencephalogram, it improves ads and branding. Then eye tracking gauge, it improves website design, ads and packaging. And then biometrics improve ad content. Then pros and cons, like you all know the difference between fMRI and EEG. fMRI gives you very good spatial resolutions, and EEG also helps you in getting a very good temporal resolution. So the pros and cons, if you see, most expensive and invasive method, less detailed than EEG, but considered the gold standard for measuring specific emotions. So like that is what fMRI does. And then for EEG, it's more expensive and invasive than many other methods, not as precise as fMRI, but can measure changes over smaller increments of time. And then eye tracking, you have the relatively inexpensive and easy to administer, and best used in conjunction with biometrics, and does not measure emotions. And then in biometrics, best used in conjunction with other methods such as eye tracking, and facial coding is, of course, it is relatively inexpensive. So these are some of the techniques we use in our lab to understand consumer behavior and their buying patterns and consumer correlates. So this is a graphical summary of consumer behavior and their buying patterns. So most of the traditional marketing methodologies, like marketing is something where people have been doing research over years. There are lots of papers on market research, and basically the traditional marketing methodology, they rely on one-to-one interaction, one-to-one interview, or they target the focus group, or they give some questionnaires, and this is how they collect the data about the consumer buying patterns or buying behavior or their feedback. So it's like collecting feedback from the consumer, how they perceive about their product or services or their offerings. So these are the methods they use, or the traditional marketing methodology they use is one-to-one interview, or they target the focus group, or they give questionnaires, and this is how they try to understand their perception, right? So all these methods are fine. Like you call a consumer to have one-to-one interaction, take their feedback, you give them questionnaire, take their feedback. All these methods are fine, but they are not that robust, because people might like your product, but they might fake while you are interviewing them. Okay, so neuroimaging becomes very easy because it's very difficult. It's very difficult to fake that. Okay, you cannot deceive that brain signature or brain signals, right? So in that sense, neuroscience and neuroimaging becomes very important to understand what exactly consumer thinks or how they perceive about a particular brand or services or the offerings, right? So that is something which most of the people now they're trying to get into neuroscience and neuroimaging to exactly understand what happens at the last minute or last millisecond when they make a buying decision, or they they try to understand buying patterns from using neuroimaging data. So that is very, very important. Also, marketers are also very excited about neuroimaging and neuroscience for two reasons. The first one is about articulation. This is again very important. The articulation is very, very important because the consumer might not be very articulate about their true preferences when they are asked to, and their hidden and their brain contains the hidden information about their true preferences and true buying patterns, and this can be used to understand, or this can be used to influence their buying patterns. And the second reason why marketers are excited about neuroimaging and neuroscience is that marketers they strongly believe that this kind of tools can provide them innovative methodologies to know about a product success in the market even before the product is made in large scale. So these are the reasons why it is very, very important. Now, we use ERP also. So it's a time, ERP is nothing but it's a time logged brain responses generated as a result of specific sensory motor event. And ERPs are broadly classified as endogenous ERP, that is your internal event, like and exogenous is the external event, like when you do like when it's an external feature of something, some product or something is kept in a shelf in a market, shopping mall. Then you see the external features, and then it takes some time. And then when you evaluate more about that, then that is your internal event, that is your endogenous ERP. So this is one experiment we did to understand the consumer buying patterns, where we showed products with logo of 94 image to 29 participants for 2 seconds. And this is the ERP we got, where we identifying the ERP component that differentiates consumer liking a product from consumers disliking a product, and highly familiar product category. So this is one experiment we did. And ERP and attentional mechanism. So ERP waveforms help study underlying cognitive processes and attention linked to consumer behavior, and ERP assists in identifying attention triggers, specifies locus of attention selection. Then the next thing, which I think all over the world people are doing, like NLP, natural language processing, CNN and LSTM, to do sentiment analysis. And this is a very advanced artificial intelligence tool being used by people all over the world to understand consumer buying patterns or their emotions. So it's the kind of emotion classification from the textual data. So the sentiment analysis is very, very important, because now everybody is on the wave, right? Everybody does marketing on digital platform, right? And when you do something on digital platform or in all those retail online shop, then you leave a digital trail, right? You leave, people can, uh, they can have the access to those data, and then they can try to understand your psychology behind that behavior or your online behavior. So your online behavior can be they can track and trace and understand your online behavior from the data using the sentiment analysis. For your information, like the whole world, like the top brains of this world, they are busy in doing only one thing. They will make you to like something or click something. So when you like something, there is a concept of like economy. When you click something, I think you are leaving a digital trail over there, right? So there are lots of data available on the web, and there are lots of online platform where you buy things, right? So let's say you have Amazon, you have Walmart, in India we have Flipkart, right? And you buy stuffs, right, from that online platform. And then then people also express their opinion about a product or services on the online platform, right? All this online retail shop or on that online platform, they have the review forums, right? People write about the review, they write about the rating about the product, they write about how satisfied they are about the particular services, right? So they leave those information on the web. And then we have a powerful Twitter API where you can use TweetPy to collect data and scrap all those data from the web, and you try to classify them and into positive emotions, negative emotions, and neutrality, right? So that can be done. So we have different social media sites where you have different information, like you have online retail shop like Amazon, they have a review forum. You can collect data from the review forum and understand the consumer behavior and buying patterns, or how they perceive about a particular product or services or the offerings, right? So you can scrape all those data. Then you have Twitter. On Twitter also people get their opinion about something. Let's say something about they say that this is something they like about the product, or this is something they dislike about the product on Twitter as well. And you have a TweetPy powerful API. You can scrap all those data, and you can use CNN and LSTM to classify them into positive emotions, negative emotions, and neutrality. So and then also we also try to understand how we best we can, and then we compute the sentiment score of the consumer, right? And we are also planning to fuse those data, like the neuroimaging data, while the subject is doing online marketing and I'm putting the electrode on the scalp and I'm doing the recording and trying to understand the neural correlates. So we have a neuroimaging data. Then we have from sentiment analysis, we have the sentiment score. So we are also trying to fuse those data, like we are trying to make a multimodal scheme of fusion of neuroimaging data and the sentiment score data, so that it will give you a better clarity and better understanding about the consumer buying patterns and buying behavior. So this is one study we did. We showed 8 commercial ads to the subject, and then we did the AG pre-processing, then feature extraction, then correlation-based subset selection, and then we did the emotional rating for the TV advertisement emotion prediction using AG signals, and we also did the regression analysis. So natural language, I think this is the thing which people all over the world, they are doing this work. And natural language processing based sentiment analysis, it's the automatic real-time sentiment analysis based on consumer, customer, product review and comments. And it is and then based on that you can do the evidence-based marketing decisions. So you have the product, then that is sold on multiple e-commerce platforms, and then you have the ratings and comments and opinion or feedback about the product, service, or their offerings. Then you use NLP-based sentiment identification framework, and finally you get the sentiment score, and then you make a decision about the product. So marketing decisions to improve consumer sentiment. So now you have the power of data and the power of analytics, right? So when you have the power of analytics, then you have lots of data, right? You have lots of data, and then people use all kind of ML models to find relevant patterns from the data. And then the marketers or the people who are really getting into this analysis to improve their product and service offerings, so they have the power of this data and data analytics, and they can make a data-driven decision. So now it is more about data-driven decisions which can help them to understand consumer buying patterns and buying behavior. Sorry, I can't move the slide. Is there any problem? Oh. Okay, so this is about marketing decision to improve consumer sentiment. So what we also are interested in the specifics of ERP-based consumer preference assessment, and for that we have used the PCN, that is your posterior contrast. So this is the recent work we have done, and some of this work is also in progress, but some of the results and findings which I like to discuss today. And this work has been done in collaboration with an industry who are into the business of AI and marketing, and they provide market insights and market intelligence to their bigger clients like Google, Intel, and Microsoft. So this study is on posterior contralateral negativity, short it is PCN. So posterior contralateral negativity, PCN, is an ERP. It elicits in the posterior brain areas and elicits between 175 millisecond and 300 millisecond contralateral to the target side. And PCN also indicates attentional focus on a target item, and PCN is independent of surrounding noise. Then posterior contralateral negativity is linked to attentional visual allocation, and thus it depicts a brand preferences. So there are lots of studies. You'll find that people have used this posterior contralateral negativity for understanding the brand preferences. And you'll find lots of marketers or market research data also that they have used this posterior contralateral negativity, short PCN, to understand brand preferences. So that's problem again. Okay. So what we did for this work, this is a methodology where we recruited 30 participants, and 18 among them they were 18 female, and mean age was 32.03 plus minus 3.3 years. And the exclusion criteria was neurological illness, history, damage, currently taking psychiatric medicine. So these were the exclusion criteria. And the procedure and task, what we did was the stimulus discrimination task. Then participants subjected to random combination of different toothpaste brand, and time was 800 milliseconds. And participant preferences noted by keystroke. And duration of task was 45 to 50 minutes. And the stimulus which we used, it's a common and very famous brand, toothpaste brand in India. That is Colgate, Mamaearth, Chico, and Pigeon. So most of this toothpaste is being preferred by, mostly all this buying decision being done by mom. Mother or mom, they take the decision, and these are the Chiku Pigeon kind of toothpaste is mainly preferred for children in India. And we did this study where we have chosen these four toothpaste brands: the Colgate, Mamaearth, Chiku, and Pigeon. So these are the four toothpaste brands used for the stimuli. You have the Colgate, the Mamaearth, and Chiku, and the Pigeon, and these are all being used by kids. These are all better blast toothpaste for kids in India. And most of this decision being made by mother or mom, they make the decision about their kids' toothpaste. Okay, so these four brands we choose, and four toothpaste brands, they are being used for the stimuli in our experiment. And this is the experiment protocol where you have the blank screen, then the fixation point. It's a 3000 millisecond, and then we showed two brands first, and the level presentation was for 800 millisecond. And the level selection, and we have not given any time limits for that. And then the subject has to press the left and right button for, if he likes it or he doesn't like it, right? So this is what we recorded, and then we found that so most of the studies where we have done this experiment on subjects, we did it in we went to the industry and we got those subjects, mostly moms and the parents, and we collected data, and we found that the Colgate was mostly preferred by these guys, right? So you can see the behavioral and easy data acquisition, where we have used 14-channel EEG, Emotive Epoch Plus, for this analysis, and acquired data analyzed using Emotive Pro Analyzer, right? And then we got this brand preference in the study, where you can see the all four toothpaste brands and brand preferences in the study, and the number of times the brand was preferred. You can make out from this plot where Colgate was more preferred brand than the Pigeon, Chiku, and the Mamaearth. Then this also gives you the understanding about the amplitude percent time plot here for Mamaearth, Colgate, when red one is from O1 and O2, and then you can see the Chico Pigeon plot, and then you have Chico Mamaearth plot, and then you have Colgate Pigeon plot. So this is something which is a very remarkable, you can make out the distinction between all the negativity and the brand which is preferred, brand which is not preferred from this work or this plot. So coming to the discussion of the posterior contralateral negativity amplitude, not larger over the contralateral sides, that is preferred targets, and posterior contralateral negativity found invariable across the four brands. And the possible explanation for that the four brand images had competing characteristics and possible competition in visual cortex, and simultaneous representation of stimuli leads to neural representation competition. And PCN elicit thus for each brand. And one more thing which I would like to add here at this juncture is about the subject, and it's not only the brand preferences. It's not only something where you can get the neural correlates and try to understand someone's brand preference. There are cultural aspects, like culture also affects the decision, buying decision. Your socioeconomic background, the culture, the language, and literacy rate is also important while doing that. So most of the subjects where we have used in this study are well-educated parents, and in Bangalore, city of India, where Bangalore is a very well-developed place in India, and we selected those subjects for our study. And this study has, like you can see from this, clearly gave a pattern that Colgate is the most preferred brand according to our study, which is being done with the collaboration with the industry. And also from this plot, you can see the comparative analysis of Mama Earth, Colgate, and Chico Pigeon, and Chico, Mama Earth, and Colgate Pigeon. Then in conclusion, I will tell that multiple modalities required to assess consumer preferences, and EEG-based analysis is suitable for scaled-up research, and ERP studies can be combined with sentiment analysis, and this is very, very important. And so ERP studies can be combined with sentiment analysis, where it is, so when the subject is buying something online, so we also did, we are extending this work where the subject is buying something online, and we are putting the electrode and the EEG system, that portable mobile EEG system, and then we are trying to understand their neural correlates. At the same time, we are also using the sentiment analysis data, but for the same product, let's say Colgate. So whatever the information about the Colgate is available on the web, like whether it's on Facebook or LinkedIn or Twitter, or on the online platform where they're buying it, like let's say Amazon platform, there are review forums. So anything related to Colgate, we can scrap those information, and we do the sentiment analysis of Colgate. And then at the same time, when subject is buying something on the platform, and let's say he's buying Colgate, so we collect the neural correlates, the neuroimaging data, and trying to fuse those sentiment score with the neuroimaging data. So this work we are extending for this Colgate brand, and seeing what happens, why it is being chosen, or why it is being preferred over other brands. So we are going to combine the neuroimaging data with the sentiment score data, and trying to build a multimodal scheme to understand and get a better clarity about consumer buying patterns and buying behavior. Then eye tracking also, we are trying to infuse with the eye tracking, which can enhance consumer neuroscience work here, because there is a strong correlation between your eye movement and cognition, right? So we were trying to use that as well to understand the consumer behavior, right? And finally, which I have not mentioned in this slide, is also about using the graph modeling. Like while during the introductory part, I told that we are using graph models to understand dementia. So we are also now trying to get into, and I also said in the beginning that we have tons of data related to brain structure and function, but very poor understanding about the exact relationship between structure and function. So we are also trying to understand the graph models, or how we can convert the neuroimaging data to graphs and networks, just language in the language of nodes and vertex, or nodes and edges, so that it will give you a better clarity and understanding about consumer buying behavior and buying patterns. Like I also mentioned in the beginning that cognition is a very dynamic, and in consumer buying behavior or making decision, right? When they make a buying decision, what happens in the brain and how it behaves. So what is the network being formed? What is the topological structure of that network being formed? I told you in the beginning that cognition is a very dynamic and distributed process, and it involves the coordinated effort of different brain regions, right? So when it with the coordinated effort of different brain regions, then there are connections being formed in the brain, right? So there are connections being formed in the brain, and then can we have that brain pathway or neural pathway to understand, hey, this guy is liking Colgate, So what is the pathway, right? So when you look at, like, we have four brands here, you have seen, right? So you have four brands: Colgate, Mama, Chiku, and Pigeon. And when the subject is looking at this, let's say he's looking at Colgate, there are different sets of neuron will get activated when he's or she is looking at Colgate. When he or she is looking at Mama, then there will be different sets of neurons they get activated when they are looking at Mama. When the subject, he or she, is looking at Chiku only, so again the different sets of neurons get activated, or they are into actions when they are looking at only Chiku, right? And let's say we have Pigeon toothpaste for children. Then when the subject, he or she, is looking at Pigeon only, then different sets of neurons they get activated. So there is a difference, and then once there is a difference in the neural correlates here, so can we have, or can we map those things, right? When you convert the neuroimaging data, let's say the subject is looking at Colgate and you have the EEG data, and you are converting that EEG data into graph and network, language of just nodes and edges, then you can also have for Mama, you can also have for Chiku, you can also have for Pigeon. Then you can do the comparatively network, you can do the comparative network topological structure analysis. That will also give you a better understanding about the buying behavior and buying patterns of the consumer. And let's say someone has just seen Colgate for the first time, then the network which will be formed in the brain will be different. If the same guy is, let's say after 1 month, he is again looking at Colgate brand, then the network topological or graph which will be formed in the brain will be different. Same thing we can say about Mama Earth, Chiku, and Pigeon as well. So graph modeling is something which people have not explored much. So we are trying to get into this and trying to make better understanding about consumer buying patterns and buying behavior using graph modeling as well. So that will give us a better understanding, and so and it will help in finding the exact brain pathway, like if it is preferred and they are liking this brand, then what is the network topological structure? If they are disliking it, what is the network topological structure? And an alignment of this network topology structure will give us a better understanding about their preferences. So with this, I think I'd like to conclude my talk and happy to take any questions. So thank you so much for your time and attention. Thank you.
Thank you, Vicky, very much. Now it's time for questions from the audience on both sides of the screen. So shall we start with the ones from the audience?
Yeah, some questions from the audience. I have a few questions. Well, Vicky, wonderful talk. This is Vasily. Few questions. Perhaps some of them are methodological in a way. So you nicely reviewed different techniques, and you focused on particularly on the neural correlates of engagement. And this idea is quite close to idea of attention, and but still engagement is somehow different from preferences. So if we, I mean, in many studies we study engagement and correlates of engagement. It doesn't 100% fit to the idea of preferences. Yeah, so you can be engaged in certain, even in certain brand, for example, that recently was associated with some scandals. So perhaps you will pay more attention to this stuff. Still, it doesn't mean that you have a strong preference for this. So do you see a problem here? Because in most of the studies, we focus on engagement. It's not 100% similar to the idea of preferences.
Yes, yeah. Thank you so much, Wesley. I think you are right on the. This is a very nice point you made about that. Yeah. So engagement is important, and preference is also important. So mostly in the Indian context, when people sometimes you buy products, sometimes based on emotions, emotional, like we have two brains, emotional brain and rational brain. So sometimes based on emotion, people buy something. Let's say my mother used to buy that brand, the son is also kind of become emotional and okay, I'll buy this because my father used to buy that. So there are different aspects also to understand. It's a very complex thing, and you rightly raised this issue, Wesley. Thank you so much for pointing this out. So preferring something and engagement is totally, it's a different picture where we get. But sometimes what happens, it becomes complex when you'll find people might not like it, but they become emotional and they buy that product. So I think that is what I can say at this juncture. Yeah.
Okay, and can I ask? Yeah, Can I ask an additional
Yes,
question?
Vasily, you ask your second question, and then Anna Ismalkova
Okay.
will ask her question.
Okay, sorry for this. Just I have few questions, but I'll ask one. Vicky, just a methodological question. So you mentioned a nice line of your research with statements analysis and natural language analysis. Can you clarify a bit? I mean, you of course can analyze comments in internet, consumer comments.
Yeah.
Does it mean that
Yeah.
you
So
somehow link brain activity with the aggregate, let's say, comments of a large population? So it's similar to kind of neuroforecasting. You forecast aggregate behavior, or you manage to analyze individual comments and and link brain activity to individual, let's say, sentiments.
yeah.
Just
So
clarify
again,
this.
it's a very nice question. Again, thank you so much, Wesley. So sentiment analysis, mainly what we do is we have tons of data about, on Twitter also people write about products. So we find those data, and we have powerful Python API like TuiPy, and we can scrap those data. And let's say I want to get data about let's say Colgate, and Colgate, anything about Colgate on Twitter I can scrap, and then we'll see what are all the people's sentiment. At the same time, like what I suggested about so sometimes it becomes very difficult. Let's say someone bought online, from the online platform, someone bought Colgate, and if he writes in the review that thank you so much for the product, okay, he has written this textual information, thank you so much for the product. So sometimes it becomes very complex to understand that, because how do I make that, whether it's a positive emotions or negative emotions? It can be, someone might have told it sarcastically also, right? Thank you so much for the product. Someone might be sarcastic also, right? So sometimes it becomes very, very challenging to do things only on sentiment. So the logic behind getting into, let's say the guy is buying Colgate on online platform, and we are putting the electrode and trying to understand the neural correlates or the maps and things like that. Then we try to understand what happens in the brain when he is doing that kind of study, right? So that is the logic of thinking of combining those both information, both sentiment score and the neuroimaging data, that will give you a better clarity about the behavior of the consumer. Yeah.
Thank you very much. Very interesting talk. Um, Actually, my question is a bit related to Vasily's. As a mom, for me, these brands are really different because Colgate is associated with toothpaste, toothbrush, and Chico is associated with high chair, with stroller, and so on. And actually, in linguistics, there are methods for semantic networks modeling, like vector graph, word to vec, and so on. So, have you considered applying model semantic network models like vector graph or
Yeah,
something?
yes, right. So very, very, very nice question on semantic network. So we are also trying to get into that's again graph models. When we talk about network, the first thing comes to my mind is graph and networks. So the semantic network would be a wonderful study which we have not explored, but thank you for this suggestion, because this work is in progress. I have not shown you all results here because still my PhD student is there at Bangalore in their R&D center collecting data. But thank you so much for this suggestion, where we can, that like Chiku or Mama Earth, where we can also think of extending it to semantic network analysis of this brand. Yeah,
Yes, I
so
think
we
it
have
would
not
be.
explored it, but we will be certainly looking into it, because we have a in-house competency in graph modeling and then semantic network. When we talk about semantic network, we can think of using graph models also. Yeah, thank you.
Yeah, thank you. It would be fascinating to see how these semantic networks will modulate this experience.
Yeah,
Yeah, thank you.
yeah, thank you so much.
Many thanks. Are there any other questions? I couldn't find any in the chat, so yes, more in the online mode, or in the offline mode.
Vicky, still a couple of questions. I will use this opportunity to ask, since you deal a lot with the industry. And for example, some of our students, they try to open companies and neuromarketing companies, and they often face a problem to use, for example, either eye tracking that is cheaper or EEG that is a bit more complicated. What do you think when you deal with the industry? What is the added value of EEG? It's just interesting since we also deal with the industry, and how do we sell this approach, because many types of analysis can be done with eye tracking.
Yes. Yeah. Thank you so much for raising this question, Leslie. So we work like 2 3 industry. We are working with them. One thing I found about the industry guys, they want things very fast, and and cognition is a very complex process, right? I told them that. So they funded our lab, and they want some results and some explanations or some insights about all these brands, and they wanted it very fast. But yeah, of course, they are also very excited about EEG and eye tracking. And so we have we trained the people also about using EEG, how to do the data acquisition, and we are extending it to eye tracking stuff also. So of course, it's now the things are changing. Earlier, people used to do only ML models or sentiment analysis, and then Google Analytics to understand consumer buying patterns and buying behavior from the online platform. But now they are more excited about neuroscience and neuroimaging, because they know that as there is a buy button on the brain, and what are all the tools and techniques they can use to understand or to find those patterns in the brain using neuroimaging and neuroscience. So they are very very excited about neuroscience and neuroimaging. Most of the marketers I have seen, and some of them are that trying to invest more in neuroimaging and neuroscience, because they are giving a project and funding labs who are doing research on neuroscience and neuroimaging in India to understand about brand preferences, and and at the end of the day they want to sell a product, right? So they need to understand that how neuroscience can help them to get a better insights and stuff like that. Yeah.
No, I
Yeah.
just ask whether there are any other questions to Vicky.
Perhaps I can ask the last question.
The
Vicky,
last
just
question,
a practical question. Vicky, since you presented many projects related to ERPs, what is your rule of thumb right now? Because I mean, about the number of trials, that is some people think that this is a weak side of ERP technique, since you have to have multiple presentation of stimuli. And perhaps I missed some of these points. Perhaps you presented them already, but what is your role in the lab? So how many times do you present the same stimulus, and do you see any problems with repeated presentation of the same stimulus many times? So for many of
Yes.
us, it's a
Yeah.
kind of a limitation of the method.
Yeah. So ERP, I think I already we do lots of ERP analysis for this consumer neuroscience research, and like you rightly pointed out, sometimes it becomes challenging. And challenging in the sense, training the subject is one challenge. When we give something to them, if they don't concentrate on that, then it becomes a challenging stuff for us. And then we have to repeat things again and do things. So sometimes subjects become very conscious. They are not very freely they are doing that kind of stuff. Then that is the challenging stuff. But if you ask me, it's a very wonderful tool for us, because suddenly you're showing something and you can mark it that it is the exogenous ERP, let's say after 150 millisecond, or when the subject starts giving more cognitive load to the brain, then you get the endogenous ERP. So we it's a challenging thing we do in the lab, but again we train the subject and then we take it forward from there. But for us, I think most of this consumer neuroscience study, and by the way, so we have lots of data, lots of updates, but since both these projects were funded by industry, we are simply providing them the insights, and we are not, as per the non-disclosure agreement, we are not publishing any results as of now because of the non-disclosure agreement with the industry, because we are using their brand and all those things, and we simply provide insights to them. So we have not published any of this neuroscience, consumer neuroscience thing, because of the industry control over this funding and things like that. But coming back to your question, ERP is very useful. Sometimes it becomes challenging, and for me, the challenging aspect is about subject training. Yeah.
Many thanks for your answers, Vicky. I think because we started 10 minutes earlier, right? Thanks to Vicky's kind agreement. So we may finish 10 minutes early as well, because we have a lunch or coffee break, right? Served in 213, right? On the other side of the staircases. So we can have then good break in order to be in time with the next lecture provided by Professor Alex Asachi on fMRI signatures in the EEG signal, right? And again, use this opportunity to thank Vicky, who gave his lecture, his talk from so far away, and thanks goodness we have this online means. Huh?
Yeah, thank you. Thank you so much. Thank you.
Britain. Somebody told me that you're in Britain. So the more so, Vicky, see you around. We're looking forward for collaboration. And again,
Yes.
many thanks everyone, and see you in an hour and quarter.
Привет.
Здравствуйте.
Здравствуйте,
Ну
дорогие
чё?
товарищи. Алексей Евгеньевич, привет.
Привет, Анна.
We have to switch to English. Hello, Алексей Евгеньевич. Welcome, профессор Асачи, on board.
Hello.
Подождите, I'm without glasses.
It's me, Anya. It's me.
Да.
Trust me.
Бота поймай. Это бот.
Вот. No, Professor Alexei Artsakhi supervises his division on brain-computer interfaces. But at the same time, Alexei has been collaborating with cognitive people at our center and the university for some time, and we have quite high affinity to each other. And today, Alexei is going to talk about a fascinating area of seeking some signatures, correlates, echo of fMRI in the EEG signal. You can imagine that it's a big deal, right? So I mean, in order to make it my introduction shorter, I think I stop here and invite Alexei to this metaphorical floor to continue with his talk. Moreover, we see your presentation very well, Alexei. So please start.
Okay. Thank you very much, Anna, for the introduction, and thanks very much for inviting me to speak about one of the recent developments of our Center for Bioelectric Interfaces at HSC that is done together, in collaboration with Artificial Intelligence Research Institute in Moscow. So the topic is, earlier there was a title called EEG-based fMRI digital twin technology. I decided to soften it a little bit because we are not there yet. We are working, but I mean we haven't yet finished the work. So I titled it as Towards EEG-based fMRI digital twin technology. Okay, so. And you probably know the conference. The conference is dedicated to ecological methods, right? To ecological methods that can be used to study brain activity. And one of the most ecological approaches, clearly, that accesses the brain is that of electroencephalography, right? The EEG. Unfortunately, EEG has relatively poor spatial resolution, but at the same time, it enjoys very high temporal resolution and allows to talk about different brain rhythms, talk about functional connectivity, synchrony between brain sources, and etc. But EEG, I think, within the context of this talk, EEG is not capable of seeing deep brain. Okay, it's very poor. It's very poor in trying to discern or trying to estimate the activity of subcortical structures and the cortical structures at the same time, or deep cortical structures such as hippocampal construction, right? These structures play a crucial role in decision making and affective neuroscience, in learning, in many other aspects. Okay, but it's been overlooked largely because of the lack of tools for studying their activity in an ecological setting. It's typically done using fMRI technology, right? Which on the one hand has relatively poor temporal resolution, but pretty good spatial resolution. But it's very bulky, it's very expensive, and it's very far from being from offering an ecological setting, right? Because you lie there, it's a lot of noise, very non-natural position, and things like that. Okay, so therefore we kind of started looking into the opportunity to decode subcortical signals that are recorded by fMRI from EEG. Okay, so but let's first see what each of these modalities measure. Okay, so the fMRI modality measures so-called blood oxygenation level dependent signal, and basically this is the signal that occurs when the blood gets deoxygenated. The hemoglobin is losing oxygen, right, and then becomes deoxygenated and changes its magnetic properties that can be picked up by the MRI machine. Okay, and when and why this happens? Well, this happens after certain population had been active for some time, like this neuron has been active for some time. There is then it emptied its energy storage, and it needs to replenish it. And in order to do so, it needs to attract more blood. That is done through astrocytic network, and this blood that is attracted is full of oxygen, and then oxygen is getting depleted in this region of the brain that has been active during the interval of during the previous, let's say, 5 to 6 seconds. So 5 to 6 seconds is important here because what it means is that the bolt signal is actually delayed with respect to the corresponding electrical activity by about 5 6 seconds. Okay, so what does EEG measure? Well, EEG, we all know that it's postsynaptic potentials, right? But the idea is that we have a neuron, we have a synapse, right? A synapse transfers the signal to the dendrite, and the postsynaptic potential starts propagating, current starts propagating down the dendrite, and if this stimulation, if this presynaptic potential occurs simultaneously or nearly simultaneously on a bunch of neurons, right? Then this bunch of neurons can be seen non-invasively from outside of the brain, from outside of the head, by noticing the difference in the potential that is generated on the skull. Okay, here you can see that the current source is placed in the middle of the head here, and the color indicates the flow of the current, and that current actually hits very poorly conductive skull, right? And it's like a light beam, right? Gets deflected from a mirror, right? The same as the current gets reflected back from poorly conductive skull, but still some small portion of it makes it out, the same as a non-ideal mirror, and does create the potential difference that we do register on the skull by placing the electrodes. Okay, so and it had been, until recently, I would say, it had been thought that electrical activity and bold activity are two complementary measurements that are on the one hand related to each other, but primarily through location, right? So that you can pick up specific location from the based on the fMRI, and then focus on that location, on the sources of that location, and to estimate, fine details of electrical signal activity in this region, right? And that's how EEG plus fMRI technology occurred, because people started to be able to record simultaneously EEG and fMRI and bold signal, so doing EEG inside the fMRI machine. I will show you how the time series looks. They look very noisy due to so-called gradient artifacts and also ballistic cardiographic artifacts that occur due to the heart being placed in the magnetic field, right? But I will but they get cleaned, okay? And more or less you have access to more or less clean EEG data and ball signal. And then there have been a lot of studies that I'm not showing here that were dedicated to combining fMRI and EEG together in order to enjoy the complementary resolution properties, right? High spatial resolution, like high, still in quotes, but let's say higher spatial resolution of fMRI than EEG, and very nice temporal resolution of the EEG, right? Uh, at the same time, the Rita school, I thought it was only in Russia, but it occurred that it's not. It's also I also saw some people from Germany that do speak about activity of subcortical structures based on looking on just the EEG signals. Okay, that made me puzzled, and I thought how it was possible. Okay, and then I started digging into this in general, and something was telling me that it will be probably very difficult to recover electrical activity of subcortical structures from EEG, just because it's all basically physics, right? And physics tells me that it's very difficult to actually get hold of signals that are so deep inside. Okay, yes, cortical signals, yes, fine, but the peculiarities of EEG, like changing from one rhythm to another, or the presence of specific number of bursts of specific rhythmic activity, or maybe slowing of the activity, some very complex, non-linear, if you will, non-linear changes in qualitative changes in EEG may actually be indicative of activity of the subcortical brain, okay, of the subcortical structures, okay, like basal ganglia and others, okay. So, but let's first go back to the cortex, right, and talk about the relation between the cortical ball signal and the EEG, right? And what I'm going to show you here now, it's not our work, it's the work of other people. Actually, there are no last names here for some reason. I'm sorry, but ask me, I will send you. But this is a relatively recent paper published in Neuroinformatics, where they show that from the it's possible to predict the FNIRS signal, infrared spectroscopy signal, from the concurrently recorded EEG data. So they use this kind of setup where they have optical leads, right, and that typical FNIR setup, and also have EEG electrodes installed, and they collect for each subject, they collect about 1 hour, 15 minutes of data, and they train a neural network, actually a very simple one, to predict cortical ball signal from EEG. Again, I'm emphasizing we are talking about cortical signals, okay, not subcortical, right? You may say why? Well, yeah, that's a good question. Except that because you can get the profiles of activity of cortical sources from EEG by solving the inverse problem pretty reliably, actually. And I'd say, with very little delay, basically no delay, and I don't know, but just this shows this method, this paper actually shows that it's possible to actually infer the ball signal from EEG measurements. Okay, and this inference carries some sort of a qualitative character. Okay, and so let's see what they got. So there are several interesting things here. Well, the black curve is the true FNIR signal. Okay, on the x-axis it's time in seconds, and the red one is the signal that has been decoded from EEG. Okay, the first thing to notice is that the red one goes ahead of the black one. Well, remember about 5-6 seconds, because hemodynamic activity follows the EEG's electrical activity. And since we are recovering hemodynamic activity from some segment of EEG data, we are in fact looking into the future of the ball signal that is to be recorded, that is to be yet received. Okay, and it's not because of the machine; it's because of neurophysiology. Okay, and then they looked at several patients, and that's the reconstruction error. So it's actually, I would say, the results are pretty good. Okay, I presume that this is a relative reconstruction error, so maximum is 1, right? So, and given that they recorded a relatively small amount of data, I think that if we do it properly, record large amount of data, do a better neural network, train it better, it will be possible to nearly completely replace FNIRS. I'm sorry, it's a provocative statement. Uh, but as far as we're talking about the cortical signals, I'm pretty confident about it. Okay, but FNIRS doesn't see anything beyond cortex, right? FNIRS sees only very superficial signals. That's why they call FNIRS as like Pullman's version of fMRI, right? So, but fMRI does see subcortical structures, right? And then it's even more interesting now, more intriguing to tackle the question of whether we are able to decode the activity of subcortical brain regions uh, from the EEG, from the surface EEG, right? Because if we can do so, then we can study affective behavior, we can study learning, we can study many other things in a very, very ecological setting, just with just a simple EEG setup. Of course, before that, according to our prospects, right, the subject would have to go to the fMRI EEG study, where we would learn a model for the subject, And then with this model and the EEG recorded in the new sessions, we will be able to recover the activity of subcortical structures. Okay. So, well, I already mentioned this, but basal ganglia are definitely one of the most interesting subcortical formations that carry a lot of function and participate in quite a bit of processes, and also have been implicated in a range of diseases of nervous systems. But again, it's quite difficult to study these structures, and I'm sure if we are to have a method that is able to get access to activity of these brain regions, more ecological and more like cheaper access to the brain regions, and more 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 available, I would say, right? Then we are going to discover many more functions of these brain regions. Okay, so that's again a kind of explanation that EEG is both cortical, EEG is cortical activity, fMRI is both cortical and subcortical, and we want to use EEG to recover fMRI signals and subcortical signals, subcortical fMRI signals. And it is theoretically possible because it's a well-known fact that there are quite a bit of projections of the subcortical structures onto the cortex. Okay, and and of course, Bolt signal is not directly related to the electrical activity or electrical activity of the cortex, not directly related to this activity of subcortical structures. The relation is much more subtle and much more complex, not just some linear or something. So we need to approach it with some more complex solutions or decision rules that would take EEG and transform it into the subcortical world, right? Also, another reason why I think it's possible is because there had been quite a bit of literature already describing the mechanisms of how subcortical signal, sorry, of how ball signal is actually not subcortical is actually not specified, but how ball signal is related to the EEG, right? And it's typically gets related to hemodynamic response function, which gets kind of convolved with absolute electrical activity of certain brain region, and they claim that it gives you EEG, or they claim it gives you ball signal. Okay, well, it's partly true, yes, but it's not that simple because to do a better job, I will talk about it later. You need to have several hemodynamic response functions that you apply to EEG filter in different subbands, and for each subband, the hemodynamic response function will be different. And actually, the higher the subband, the closer the hemodynamic peak, the peak of the hemodynamic response to the origin, to zero. Okay. So, but there was another hypothesis that was pushed forward by I think it was Bill Penny and Preston. They had this paper a long time ago. They were saying that the increase in Bolt signal is accompanied its frequency here. So I'm sorry, it has to be omega, right, or f, right? It's accompanied by the spreading out of the spectrum of the EEG spectrum. So as our EEG spectrum moves to the right or spreads out, we are witnessing the increase in the Bolt signal. Okay, that's another hypothesis, and I think this hypothesis fits more maybe the resting state EEG Bolt relationship, while the former one fits better the evoked response kind of. I'm sorry. Uh, and I'm sorry. Yes, I'm sorry. This is what happens when you don't study learning in dogs. Okay, so the basic idea here now is to take EEG signal, is to take the subject, put him or her into the scanner, record simultaneously EEG and Bolt signal, and then use machine learning tools to decode Bolt signal from the EEG, and then use this model to then record about to transform the cortical, not cortical, sorry, the scalp EEG data into subcortical activity, but bold activity. Why bold? Because bold is slow and EEG is fast, and this is technically many to one problem because we have many samples of EEG, and we want to to transform them into just a single sample of bold signal, right? Because bold signal typically sample maybe twice a second, maybe three times a second, right? And an EEG sampled at 250 at the smallest, right? 250 samples per second, right? So it's a many to one problem. It's pretty tractable. So here is the schematic representation of it. Yeah, and then basically when you're done, you can record EEG, and you can apply your machine learning model and infer subcortical structures. Then you can apply it into a range of things like from affective BCIs to fundamental research, neuroscientific research in an ecological setting. Okay, so now that was a long introduction, but now I'm going to tell you actually what we have done. We've taken this data set that has been recorded with so-called carbon viral loop technology, simultaneous EEG fMRI data set. This is the approach where you place specific additional loops on your head, on the head of the subject, so that they can pick up the artifact signal, but of course they are not picking up any electrical activity of the brain. And then you can use the signals picked up by the CWL loop to subtract them adaptively from the EEG signal that is contaminated by the gradient artifact. Okay, so you're taking this, and the data set has pretty small number of data. Okay, it has 8 subjects and only 5 minutes per subject. Now we are, as I tell you, we are working with much bigger data sets, and we are also able to record them together with Pavel Rudic from Novosibirsk Tomographic Center. Okay, and also we found another relatively big data set that is now available online. So we are experimenting with it. Okay, so let me go. Let's see. Okay, so this is how the data look like. Okay, this is where there's no gradient coils turned on. This is where gradient coils get turned on, and you get this horrible high frequency, actually very broadband artifact here that you need to get rid of. And so that's what we approach. We first get rid of this artifact. Then we clean EEG a little bit, remove artifacts, remove like additional artifacts. Well, we also take fMRI signals and we do standard processing to the ball signals, right? We do regression of motion parameters. We remove mean common mode signal, which would reflect the activity of the white matter that is present in abundance, right? And then we also some but more or less standard things that are used to process both data. Okay, and then we use the atlas, and then we extract the activity of subcortical structures. Okay, all these, and also hippocampal structure. So that is not subcortical, but deep cortical structure. Okay, then since EEG and BOLD are sampled very differently in time, we do interpolation of we decimate EEG and interpolate bold signal so that they are on the same scale. And then we also do time delay correction. So we shift bold signal with respect to EEG by about 6 seconds, okay? So that we can our receptive field of the network is covering the time interval of EEG signal that is responsible for that ball that, remember, is shifted by about 5-6 seconds in the past. Okay, so yeah, this is just more steps because that was yeah. So anyway, so the overall model architecture worked like this. I could not go into details here, but I will just state a little bit of it here. So we do EEGs and we do feature extractors that I will describe to you next because it's an important step that allows us to interpret the obtained decision rule. And then we have, of course, bold signal. And what's interesting that what we are using the clip, what's interesting, we are using clip loss. Okay, the clip loss, probably those who are familiar with machine learning, they probably know what it is. But the idea is that we derive certain internal representation of our EEG data, some vector in a, like, say, 64-dimensional space, right? And we derive also some internal representation by more or less the same set of how I call layers, right? But of course, they're tuned to different time demand, time slices, etc. Of course, this is all taken into account. But anyway, then you arrive into another 64-dimensional vector. And clip loss tells you that if you take the same segment from the data, the basically both segment corresponding to EEG segment, then their internal representations have to be as similar as possible. Okay, and if you take non-overlapping region intervals, basically both segment from somewhere far away and each segment from another far away. The distance between them doesn't have to be small. It can be actually far away. Okay, it can be quite long, right? And quite large. Because this idea allows to learn from data in an unsupervised manner, basically, right? So we can basically take the two signals which correspond to each other, and then we can identify the parameters of these encoder networks, right? And this is just to give you an analogy. The clip loss is used, for instance, when you are using images and texts, okay, and then you want to learn generate images from the text. Okay, so you first do the thing. Instead of EEG, there is a text, for instance. Instead of bold, there is an image. And you do encoding, and you want to bring the descriptions, internal descriptions in this embedding space. You can bring them of the same pictures. You want them to be close, right? But they are taken from different pictures. You want them to be far away, right? And then you can do things, for instance, like you can write a description and generate the image based on the description. Or on the contrary, you can give it the image and it will generate the description, because it will find you the best, generate the sequence which has internal representation that is closest to the internal representation of the image, right? Okay, so and the goal of our signal is again the brain structures, the subcortical structures, and we predict the ball, and then we compute the negative correlation loss, and there we go, and we train this network. Okay, so what's important is that we, as the feature extractor, we use our interpretable network that comprises spatial filtering. So basically, we take EEG signals and lump them together with a set of coefficients. Okay, and these spatial filtering coefficients, as we call them, they can be then interpreted to tell us which brain region this source is coming from. Okay, and also we have a temporal filter, that is bandpass filter, that based on its coefficients. It's not necessarily bandpass actually, but it's just temporal filter. But based on the coefficient of this filter, we can talk about dynamical properties of the time series of the source. Okay, and it's actually where the results are pretty interesting. I will show you now. Of course, they're still preliminary, as we need to obtain the same thing with much larger data sets. But yeah, okay, this is how the clip loss looks. Okay, so the diagonal, basically, which means that similar segment and similar EG segment, similar bold, give you pretty high correlations around the diagonal here. Okay, small distance, small cosine distance, and for all diagonals, things depends, but very rarely we get as high as here. Okay, as of the diagonal, right? Which is a good sign. Okay, and then the result that we have obtained, that those are again different brain structures, left and right, and those are the correlation coefficients between the true bold signal and the recovered from EEG. I'll tell you one more thing. Important line is the bottom one, is the average. These are the time series of subcortical brain regions from which we have subtracted the average of all these brain regions. Okay, so we first extracted both signals from each of the structures, then we computed the average, like common average montage in EEG, right? And then we subtracted this average. So basically, these are the correlations of the deviations from the mean signal, or activity of different subcortical brain regions. And this is the mean signal itself, and this is the accuracy that we recovered with. Actually, to me, it was a little bit surprising, because I thought we would recover this bold the average ball much better with much higher accuracy, but it may be due to the fact that we have removed already quite a bit of common mode activity like white matter signals, things like that, that in many other studies that try to tackle, not many, but several only exist, that try to tackle a similar question, they just simply don't do it, okay? So, like for example, in this study by I think this Telma Handler group from Israel, they would had a neurofeedback study based on this, and this is how the signal, the ball signal, and how the predictor signal look. But it's for amygdala brain region, but they clearly they have very high correlations, about zero point 0.6 or something. We observed like 0.3, 0.4. But I'm sure they were not subtracting the common signal, because they were looking only for a single brain, subcortical brain region, just amygdala. And so, well, it's very questionable. Then there's another study by this group, very recent one, just maybe like a couple of months ago. They were tracking the activity of the striatum from EEG, and they were learning to decode the bold activity of striatum from the EEG signals, and they have achieved on average 0.26 correlation. We didn't put striatum here because we didn't know about this paper when we were doing this, right? But we will, of course, reduce and check. But that's the correlation coefficient they have, and this is how it changes if you move EEG versus bold, right? If you move it away, of course, with 6 seconds approximately delay taken into account, okay? So that's basically here what you see on the laterality here is chance level accuracy in their study, and this one is what they have achieved when the data were properly aligned. So this is our time series. I will show you later, but I just want to show you the following, because it's related to the test. So in order to test for the performance, we have flipped EEG data with respect to fMRI data. Okay, just flipped in time, meaning that we have just destroyed the relationship, the temporal relationship between EEG time series and the fMRI time series, and we have observed significantly smaller coefficients and basically random, like negative, small positive coefficients. Whereas when we are doing it with the proper alignment, we get coefficients which are quite high, quite high. Okay, and again, this is still a very preliminary result. It's not yet. I mean, it's a lot of things to discover, but just to show that the general direction that we're aspiring at. Okay, and one other thing that I wanted to talk and I wanted to emphasize, what I've just shown to you, it's the results of decoding of data in the resting state setting. Okay, so it's a resting state, meaning that there is no task, because if there is a task and you are learning to predict bold signal from EEG, you may be very well learning to predict simply bold signal based on the task, right? Why you need the EEG, okay? So all you need to just you need to infer from EEG that the task is there, which is very simple if it's a motor task, for instance, and then all you need is to activate the proper brain regions, right? So it's a bit of cheating here if you do it this way. I mean, it's not per se cheating; it's just a different setting, right? But the ideal setting would be to learn the model from the resting state data, okay? And then apply this model to the task data, right? For instance, motor task or visual task or decision-making task or some other emotional task, whatever. And then infer the bold signal of the task data from the EEG and compare it to the bold signal, to the actual bold signal. That will be the most honest test. That's what we are going to do, like, I think by, I don't know, maybe in half a year, since we have to be done with some main experiments on this. I'll update you on this. Okay. And then interpretation, the final step, and then that's it, and we are done. Okay. So interpretation is actually very interesting. Here are the power spectral densities of the cortical sources that the actually, no, this is not the convolution filters. Okay, so these are Fourier transforms of the convolution filters coefficients. Okay, that basically tells you that for the green one, it tells you that this filter is passing the signal in this band, okay, and stopping the signal everywhere else. Okay, for the blue one, for instance, this blue one, is passing the signal within this band and stopping everywhere else. Okay, the red one the same. Okay, so and then for each of these guys, there are spatial patterns because we have our architecture such that we have spatial filtering and then temporal filtering. Or you can think of it, temporal filtering first, and then specific to this temporal filtering, specific spatial filter, right? But what's interesting is that we have certain topographies. These are topographies of the sources that the network gets tuned to. Okay, that you can solve the inverse problem and find where the sources are, but you can observe that these topographies are very similar except for the sign, right? But because we are working with envelopes, okay, so sign doesn't matter for us. So they're basically the same, and it tells you that branch 10, branch 0, for instance, and branch 10, okay, the branch 0 and branch 10, they well, branch 0 and branch 10, right? They look into the same brain region, basically, but they focus on different subbands. And in fact, this may correspond to the fact that this construction, that network designed, devised, is measuring the expansion of the spectrum of the EEG signal, right? Because in one condition, if there is main activity is in this band, and in another condition, when bold is present, the activity is spread, it was here and here, then subtracting signal from this filter to the or this filter from that filter will give you the extent to which the spectrum gets spread out, right? Now, see here. So if you have a filter here, and if you have a filter here, and then if this activity is coming from the same brain region, then basically the presence of these two filters makes you think that the network may be looking actually for the difference, for the fact that this peak is moving to the right, if you and comparing to the fact that when this peak had been it's been located in its like original frequency, right? And these bandpass filters, several bandpass filters, allow you to track the spectrum expansion. And that's why I believe that from our data that we have received, actually the spectrum widening hypothesis is the one that is working, or the one that network got to learn. And that's maybe because we were working with the resting state data, and that, as I mentioned to you, the spectrum widening hypothesis is more closely, more affine to describing changes in EEG due to the increase of bold signal um, in the resting state setting. Okay, so and the last slide, basically, you probably know we have been active in this neurofeedback kind of research. Okay, where we where we basically take the activity of the brain and show it to the subject and ask subject to learn to condition it, okay, to increase it or to decrease it, okay. And there's also a very spread out technology that is called fMRI neurofeedback, okay, bold neurofeedback, where you do the same thing, but you are registering the activity, the bold signal, right, and not electrical signal like an EEG, but the bold signal, and asking the subject to tune the signal to tune the signal, right? So to train to control it, to learn to control it. We've shown in our research that the delay between the event in the brain and the moment when the subject sees the feedback is actually crucial for the success of the training. Okay, uh, and if you now and that we have done this in EEG setting. Okay, but now if you can transfer this result into bold signal setting, right? And then you remember that one of the first pictures where decoding from electrical activity gives you advanced access to the bold signal, so you see it earlier. Uh, then maybe fMRI neurofeedback thing can be redefined based on this, and its efficacy can be even further increased if you are using not bold signal that you record from the scanner, but the bold signal that you decode from EEG using the ML model, either for a particular subject or in general. By the way, the results that I've shown to you, they are only they're almost out of sample. Basically, we trained on n minus one subjects, on the whole data from n-1 subject, n-1 subject, and a little bit of data, like maybe 1 minute from the subject that we tested on, and we tested on that new subject, basically, nearly new. Okay, so they're almost out of sample, and they will be, of course, improved if you get more data and if you try to for a subject-specific model, which is not a big deal, I think, for this particular technology. Okay, so basically, what I told described to you is try to convince you that it's possible in the future to create a fMRI digital twin that would use only EEG signal and the machine learning model that has been trained from concurrently recorded EEG and fMRI that can be done once for subject. Uh, and this setting will be able to replace the bulky scanner in the experiments that require ecological setting, like many of them that we do in our institute. Okay. So with this, I would like to tell that, of course, this is done by many people. Primary people who work on this is Nikolai Dagaev and Ilya Simenkov from AIRI. And yeah, we're also collaborating with Pavel Rudic, as I mentioned, from Novosibirsk. And with this, I would like to thank you. And yeah, I will be very happy to answer questions if you have them.
Okay, some questions from the audience. Perhaps, yeah.
Hello, thank you for the nice talk. You mentioned that you used resting state data and that if it was event related, maybe it would be some sort of a cheating. But what if we go somewhere in between? And again, I mentioned it because of like the logo of our conference, how we study ecologically valid settings. And I was wondering if you had some kind of naturalistic stimulus, like a video or an audio narrative that doesn't necessarily evoke like event-related activity per se in specific
Mm-hmm.
moments, would this methodology be applicable? Because then we could also study some, you know, like some areas that we know, for example, when they would be responsive, particularly, and maybe it would add some more information to the whole story.
Yeah, absolutely. Yeah, thank you very much for the great question. Yes, when I mentioned rest in state, I mentioned, well, of course, it should be, I think, and this is yet another research area, right? This has to be some sort of augmented rest in state, right? The subject is lying in the scanner, you show him videos, you play some sounds, you do tactile stuff, you do many other things, okay? So maybe it's tactile stimulation, as I said, maybe something else, right? Maybe, and then you construct this big model and then you can use this model to then already infer the activity, the subcortical activity uh, in a range of settings, right? In a range of paradigms, including this visual paradigm or tactile paradigm, whatever. And it doesn't have to be necessarily steam locked when you do this resting state, right? It just happens, right? It just happens. The brain reacts, and you're kind of the network is looking for your learning to decode this, right? When you say that when you do images, right, and you show videos, and then, for instance, you are interested in faces, right, or you are interested in some I don't know, in some scenarios that you are looking some unpleasant pictures, for example, or on the contrary, pleasant pictures, or something else, right? Then yes, you can probably. I know we haven't done yet this particular thing, right? But I can imagine that you can train the model uh, to decode brain activity during movie viewing, right? And then you can already apply it to the EEG data when the subject is viewing the movies and analyze the subtle differences, right? Not just the subject that, yes, his visual cortex is activated, well, obviously, because he's watching something, right? But that certain brain structures, some subcortical structures are activated in response to the content of the video. Yeah, I think it's entirely possible. Yeah, and I believe that of course, it's an open question. Our goal is to create the enabling technology, basically, to show that it's possible to devise several paradigms, and then yes, it can be altered according to, for example, as you suggested. Yes.
Other questions?
Hello, thank you for an interesting report. I wonder if this technology can be used only for research purposes or also for some clinical purposes in the future.
I would say that, well, see, okay, this may be a little bit like kind of blue sky, right? The horizon thing. But I was thinking that, for example, you can have a subject, a patient, who lives far away, or actually you can have an astronaut, right? Or you can have a a person who is exploring Arctic regions, right? So you can you can create a model for this subject, right? It can be a patient, or person who is working in extreme settings somewhere where you can't put an fMRI scanner. You can create the model for him or her, and then she, for example, if it's a patient, or he can go home, and at home he gets access to EEG, which is not a big deal, it's cheap. And then you apply the model, and you can verify the activity of his subcortical structures if it's needed for monitoring of his illness, for instance. Yeah, I think it's possible, definitely. And here we can, I think we can simplify things because we will be looking for this subject specific model, right? But then the big question here is, for example, if you have a patient, right? The patient has some problems, right? Some abnormalities in activity of subcortical structures, right? And also in the entire brain, in activity of the entire brain. And then you learn the model for him, right? And then you put him or her on some certain medication, for instance, or you prescribe him exercises or whatever, and then he does those, and then his brain changes basically, right? For instance, his subcortical structure activity improves, right? Um, that's I'm wondering actually that this model will still be working, okay? And that's a big research question. I would say, I first said that yes, definitely. Well, yes, it's possible, but it really needs to be researched. It really needs to be checked, because if you, for instance, if the therapy will alter the brain such that the model stops working, then of course it will not be able to infer the subcortical structure activity. Yeah. At the same time, if the relationship appears to be more robust than that, then it may be possible. Yeah.
Other
But that's a
questions?
good question. This is like
Alex,
deeper
thank you
than
so
I thought
much.
first.
Yeah. Other questions? So I have a question, also one question on behalf of Anna. Alex, fascinating talk. Correct me, please, if I misinterpret you. Yeah, since
Okay.
it's a complex approach. So we have your technique, and we more or less can, let's say, have a data set of participants, train the system. We can send our participant for 1 minute simultaneous recording of fMRI and EEG, and we will be able to invite this person for only EEG study and infer.
Yeah.
Okay. Am I correct that still will not be able to use it for functional event-related studies? Yeah. Only for
No. Yeah, here. No. But see, almost correct. Okay, so first, not 1 minute. I would say 1 minute would be too good. Maybe like I don't know. As I showed to you now, result from 5 minutes, right, per subject, right? But if you have pre-trained model, then yeah, I think 5 minutes will be enough, and the quality should be quite high. Okay, but our dream is to actually train the model on the resting state and have it up and make it applicable to event related data. So you train it on a resting state, or as the first person who asks the question, some augmented resting state, right? And then it should be applicable to the task related setting, right? So basically you can learn EEG to subcortical bolt model for the subject, or even cortical bolt, doesn't matter. And then you can use this model. Then you can record only EEG for this subject, right? And then apply the subject specific model and extract subcortical activity, for instance. Yeah. And
So-
measure that in some setting, for instance, subcortical activity is higher, in some settings it's lower, and then you can contrast them and make some like more or less traditional neuroscientific inferences.
So just a clarification question. So in theory, we can make a project when we train, let's say, for nucleus accumbens, resting state activity. Also, we make another functional combined fMRI EEG study, and we try to predict based on EEG signal.
Yes.
Okay.
We can try, for instance, see, the valid test in event related setting would be this. you record it in the event-related setting, let's say nucleus accumbens, right? And let's say it's involved in what? Decision making or what? Affective something, right? But you can have different like kind of stimuli that activate nucleus accumbens to different extent, right? And so you can train it based on the smallest level of activation and on the highest level of activation, for instance. And then you present, or then you already remove the subject from the fMRI, put the EEG back on, and then you try to you present the subject the condition which activates nucleus accumbens to the extent that is in the middle between the first two. Okay, and then you are able to see it. Then this will be a very good test for this technology.
Okay,
Yes.
nice. You have a question. Anna asked me, why don't we make these experiments with our FNIRS machine, Alex?
This is basically very possible. As I mentioned, people are very successful in this, but it's the reason. Actually, yes, I already was looking when I think I was during the when I was presenting, we were presenting the topics for the students. One of the topics was that we have a lot of fMRI EEG data, and we have already the neural networks that can probably convert one from another, right? The EEG from EEG, they can convert fMRI. Oh, FNIRS, sorry, FNIRS. Yes, it's entirely possible. The only thing that I mentioned, it's not very, I mean, it's interesting, but it's not very useful because you can infer cortical activity based on EEG alone quite well. Why would you need to, just to prove that FNIRS is useless? Sorry.
Yeah, okay, of course. I mean, I see the point. So if we go to deep structures, we need fMRI. See your point. Anyway, I
Yeah.
think it would be nice,
Yeah.
nice to use at some point some of our equipment. Alex, thank you so
Yeah,
much.
yeah.
We have to stop here. We have a tight schedule. Fascinating talk. We're looking forward
Thank
to
you
some
very
new
much. Yeah.
presentations. Alexei, have a nice day. Thank you so much. And
you.
we move to the next talk by Yanis. And Yanis will make a presentation. I think it's a data set that you just presented in Canada. And I'm looking forward to your talk. Yeah.
Thank you very much. Hello, everybody. Let's see. Can you make full screen, please? It's view and the first slideshow. Okay, it works. Okay, hello again. I made the same, not the same presentation, actually a shorter version of it 3 days ago. And now I would like to also get your feedback. So we studied in my lab what are the neural mechanisms underlying the persuasion by naturalistic healthy eating goals. And I will start with a video. This is Jamie Oliver. It is a chef, but also an activist. And this is his TED talk that gave him an award.
For me, there ain't no need to flavour the milk, okay? There's sugar in everything. I know the ins and outs of those ingredients. It's in everything. Even the milk hasn't escaped the kind of modern day problems. There's our milk, there's our carton. In that is nearly as much sugar as one of your favourite cans of fizzy pop, and they're having 2 a day. So, let me just show you. We've got one kid here having, 8 tablespoons of sugar a day. There's your week. There's your month. And I took the liberty of putting in just the 5 years of elementary school sugar just from milk. Now, I don't know about you guys, but judging the circumstances, right, any judge in the whole world would look at the statistics and the evidence, and they would find any government of old guilty of child abuse. That's my belief.
Add it. Yes. So this is, well, Jamie Oliver. And this talk actually gave him the award. This is just part of the talk, of course. But the main thing is that at the end of his talk, he wished for the support of everybody to create a movement to fight obesity. And just in a very short period of time, he had 800,000 people following him. And actually, up to this point, he has more than like 15 million people following him. And it is really fascinating if you think about it. How is it possible just by talking for 15 minutes and make a point to induce such a massive persuasion? And what he did in this video, basically, we can say that it is a health eating call, okay? And health eating calls in general have been found to be very effective, okay? It's not just by inspection, but also scientifically. And there's this meta-analysis by Cantario and Chandon showing what is basically how effective different types of nudges are. And why we focused on health eating calls is because if you look at the rest, they aim at a very short-term manipulation. For example, if the healthy food is in bigger portion, you might take it, okay, because it's more food, but your opinion doesn't change, your mindset remains. But with a health eating call, basically we induce this private acceptance of, I don't want to eat sugar anymore. Um, and I want to present, for example, one study, just to show you, like in practice, how it works. This is a study by Hyde and colleagues, 2020. They presented some unhealthy food, and after that, they present some statements together with some audio narrative that, you know what, this food does not actually taste how you believe. It's not as, I don't know, it doesn't make you fun and all that. So they try to change the perception, the judgment of this food to the participants. And then they had a control group that did not receive any type of intervention. And then they asked participants basically to rate the perceived tastiness of this food before and after all these interventions. And they found that the intervention group significantly decreased the perceived tastiness of this food. So the judgment of these subjects of the food changed significantly as opposed to the control group. And we got this series of ideas and we applied some behavioral study ourselves last year, and we specified it to sugar because we identified a gap in this particular ingredient in the field. So what we did, something very similar, instead of asking before and after the intervention the participants to rate tastiness, we asked them to indicate how much money they are willing to pay in order to purchase these products at the end of the experiment. And the intervention was a narrative by a doctor, like a lecture, that sugar is bad. Yeah, like similar to what you watched at the beginning, but a little bit less playful, let's say. And the control group just listened to a narrative about photography, completely irrelevant to food choices. And what we found was just similar to the previous study that there is a behavioral effect, like the group that received the intervention significantly changed the willingness to pay for sugar. So we have this series of studies that show not only the willingness to pay, but also judgments of foods can be affected by health eating culture. But the question now is, how does this happen? Like, how does the brain respond to these messages so that the persuasion emerges? And there are not many studies actually specifically about the persuasion by naturalistic health eating goals. So we will have to go back to the literature and see, in general, what are the neural correlates of persuasion. And there are a lot of studies in this field. Also, many people from our lab have been leading scientists on this topic. And this picture basically summarizes all the findings. So there are 4 categories of regions that seem to be responsive to persuasive messages. Some regions that are specifically hypothesized to be involved in medalizing theory of mind. For example, you have here the temporoparietal junction. This is basically active. This plays a key role if you are the persuader, if you are the person who wants to persuade others. This area basically can predict how effective you will be in achieving this goal. Then you have some hypothesized self-related processing regions, like the middle prefrontal cortex, for example. And then you have valuation regions like VMPFC, the ventromedial part of the prefrontal cortex, ventral striatum, regions that we know that they're responsive in this valuation, expected rewards, and processes like this. And finally, you have this category of regions that seems to be involved in conflict detection. If you see something that, for example, contradicts with your own beliefs or whatever. And this is mainly the anterior cingulate cortex and the anterior insula. So I just put some example studies there, but there are much more supporting these regions. It's not that every one of these studies found all these regions. Every study would find one or two, but summarizing and by doing meta-analysis, we know more or less that this is the map of persuasion. And I want to just give an example of a study just to understand what we mean by persuasion in these studies. There is this neuroimaging study by Emily Falk. They examined whether we can influence people to use more sunscreen. Okay, we move a little bit beyond the health eating course just to show you that it's not specific to eating what we talk about today. So they asked participants, how many days did you use sunscreen the last week? Then, while in the fMRI, they present them with slides saying that it's actually very good for your body to use sunscreen and it's healthy this way. And after a week, they recorded again the self-report uses of sunscreen. And they found that participants were influenced, and the next week actually they started using more sunscreen. But the key idea was to also see whether some specific brain area, while viewing these slides, these persuasive slides, could predict this persuasion-induced behavioral change. And they found this region here is the ventromedial prefrontal cortex. They call it medial prefrontal cortex, but okay, it's like a big ROI here that I present you. And they found this nice positive correlation. So in other words, when you look at these slides, persuasive slides, the activity that they elicit in the ventromedial prefrontal cortex predicts whether you will be persuaded by this slide or not the next week. And not by just some rating, intention to use sunscreen, but actual behavior in real world. It's quite fascinating. Now, having said that, I want to ask you a question. If the VMPFC is so much involved in persuasion-induced behavioral change, what do you think would happen if we have a patient with a lesion in the ventromedial prefrontal cortex and we present them with a persuasive message? Any ideas? No effect, one idea we have here. So no matter how reasonable the arguments I'm using, you will not be persuaded. You will always have the same ideas. You agree? Very easy to persuade. Okay, let's see. Let's test. Yes. Studies suggest, actually, this funny word I learned last night, actually, credulity. It's a tendency to be too ready to accept that something is true. And you are susceptible to misleading ads. Yes. And there is this study by Aspen colleagues, 2012. You have here in pink, healthy controls. You have in blue, patients with damage to the VMPFC. And they presented them basically misleading advertisements. And they found that, based on self-report after the experiment, the patients believed that these advertisements contained a significant amount of truth inside. And also they had higher intention to purchase these products that were misleadingly advertised. So it's a bit complicated now, I guess. Yes, on the one hand, we see that VMPFC basically is involved, positively correlates with persuasion-induced behavior, but also if you have impairment there, also you are more susceptible to that. So one possibility why this can happen is that perhaps this is a very multitasking, let's say, brain area, and can be flexibly recruited either to comply with persuasive messages or to resist them if they are misleading. So this area might play also a role first to judge this persuasive message, whether it is reasonable, whether it is true, perhaps not by its own, but by its connectivity and its interaction with other regions in the area. And this is exactly what Cooper and colleagues tested in 2017. I was told about the study in the conference in Canada. And they said, okay, maybe BMPFC by its own, its activity in isolation does not contain so much information about this persuasion-induced behavioral change. Maybe we also need to look at how it interacts with other brain regions and altogether take this information and try to see how participants are influenced. And they found that actually this behavioral change is also associated with the connectivity, functional connectivity between VMPFC and ventral striatum. Although this has not been replicated by other study, but it is a good first step, let's say, to not look at local activity solely. So let's take two key points from previous studies. First, valuation and error detection brain regions seem to play a key role in persuasion, especially the VMPFC ventral striatum and anterior cingulate cortex. And there are some mild evidence that these areas may not work in isolation, but how they are connected to each other may also determine whether the persuasion will be successful. Now, let's identify the gap before we move to our own study. All the studies that I described to you are based on blocked fMRI designs. Okay, so basically, you have a specific period of time that the participant either watches a slide, persuasive slides, or listens to a very short narrative, like 6-7 seconds, and then they take this average within this trial, temporal average, and they compare between conditions, for example, or they just take the correlation with some behavioral change. But there is a possibility that maybe in real life scenarios, the response to persuasive messages may change as a function of an evolving narrative context. So if you consider all these fluctuations across time as noise and you just average them, you may lose some information. So our idea was that maybe if we use some more naturalistic data analysis method, as I will present you later, maybe we might be able to identify something beyond what has been found already, or maybe we will just replicate the previous findings. So this is the novelty, basically, to just use naturalistic health eating call and subsequent naturalistic data analysis method. So what we did was an fMRI experiment in the Center for Neurology. It's here in Moscow. This is the scanner, the very scanner by which we recorded the activity of our participants, 50 participants, healthy. And all of them mentioned that they eat sweets in general. Why we did that? Because we wanted to exclude some participants that might be completely against sugar consumption at all. So any intervention wouldn't have any sense. And we also asked them to be hungry when they come. Okay, to not eat anything for at least 3 hours, so that when they see these pictures of food, to not be completely, I'm not hungry, I don't want to pay anything for it, and therefore the intervention would be ruined. And this was not our idea. It is some procedures, some criteria that we followed from previous studies, especially by Hilke Plasman. And inside the scanner, we asked them to participate in a bidding task. So participants watch pictures of products. Some of them contain sugar, others are sugar-free, and others are non-edible. The latter serves as a control condition. And then they indicate how much money they are willing to pay in order to get this product. Fixation cross, next trial begins. Okay, it's a very simple task. And they perform 2 blocks of this task. One before and after, and one after listening to the narrative, what we call the health eating call. And this is the key component of this experiment. Yes, it's our intervention. Now, I want to mention that here we don't need a control narrative like I introduced at the beginning, because now we have this control condition of non-edible products, so we can correct for any effects of no interest based on that. So the idea is that we want to see how the willingness to pay changes. Okay, that's what we measure, the willingness to pay. And what we call delta of willingness to pay is the willingness to pay for a product category in the second block minus the first block. And we do this on average for every category and for every participant. Okay? So this is the dependent variable. I want to also talk a little bit about the health eating call because it's very important for this experiment. What is this health eating call? What is it that makes it so inspiring and effective? And we use it again and again. It is a 7-minute audio lecture about the health consequences of sugar. This is already a novelty because all the previous studies used very short interventions. Like if it was audio, it would be for a few seconds. And now we have this long-lasting 7 minutes health eating call that basically allows the participants to be engaged and involved in and exposed to a lot of arguments and perhaps be further persuaded. It contained arguments from scientific sources, so it was true arguments that contained this health eating call. It was narrated by a nutritionist, or at least this is how we introduced the narrator to the subjects. And finally, in our pre-test, we found that it elicited significant amounts of fear and sadness. It was not intentional when we were creating the health eating call, but it happened, so we must report it now. Now, having these attributes of health eating call, would you guess that it would be effective? And what we can do is we can ask an expert in rhetorics. Here's this guy. In case you didn't understand, this is my great grandfather, Aristotle, who wrote a brilliant book about rhetorics, yes, more than 2,000 years ago. And he said that what constitutes effective persuasion is 3 things. First, the logic of the arguments you are using. Seems like we have it. Ethos basically refers to the credibility of the speaker. And finally, pathos, the emotional appeal. So if we would ask him, would this health eating call be effective? He would say, of course. And he would be right. So here we see the behavioral effect of the health eating call. Participants basically increased the willingness to pay for sugar-free products after listening to this health eating call. Now remember that this delta of willingness to pay measures the after minus before the intervention. Relative to the control condition of non-edible products, but also relative to the sugar-containing products. So okay, we have the behavioral effect, and then we want to see whether this behavioral effect was consistent across all the products. We asked participants before the scanner to rate the perceived tastiness, sweetness, and familiarity with all the products that we used in the experiment, so that we see if this behavioral change that is induced by the health eating call happens regardless of the perceived tastiness, sweetness, and familiarity, or whether this moderates the effects. And what we found was that participants not only increased the willingness to pay for sugar-free on average, but they especially did so in products perceived as tasty and not sweet. Okay, now we finished with this behavioral data. We had the behavioral effect. Now we want to see at the brain responses. Remember that this is an fMRI experiment. So what we did was to segment the exact period of the health eating call while participants were in the scanner. Okay, so this is when the health eating call starts, this is when it finishes for every participant, and we extracted from specific regions of interest. Okay, for this example, I'm using the posterior cingulate cortex. And what we do is a method called intersubject correlation. So instead of averaging this temporal response, just like previous studies, we want to see how they correlate between participants. And this is an indicator of reliable responses to whatever stimulus you're experiencing. So it's a very simple approach. You just take pairwise correlations. Okay, just simple Pearson's correlations. And you create this pairwise matrix. And then you can do this for many different brain regions. What we used was the automated anatomical atlas 3, the last version. It's a very popular anatomical atlas of the brain. that divides the brain into 166 regions of interest. Okay, brain regions, basically that are non-overlapping. So if we repeat this idea for every region of interest, we will have a pairwise matrix for every region of interest. And if we take the average of this matrix, it will no longer be pairwise, but it will be the overall inter-subject correlation across the whole sample, like all participants, how synchronized their activity was in a specific brain region while listening to the health eating call. Okay, it's a very similar methodology. And these are the results. Now, I regret using very light colors in some areas, but maybe if you move your head, you will be able to see it. So we got these 6 areas that I indicate that exhibited significantly higher than 0 inter-subject correlation while listening to the health eating call. So in other words, these are the brain areas that were particularly responsive to the persuasive message, okay, across all participants. We get temporal lobes. Why? Speech. It's an audio narrative, yes? Participants listen to it. If it was a video, we would also get some occipital lobe, yes? Yeah, so this makes sense as a pattern. But what was important for us was to not stay only there, not have limited inter-subject correlation just based on sensory, but just based in sensory areas. We want some higher order brain areas so that we make sure that participants are engaged and they are thinking about it, they're being persuaded perhaps. We'll see later. And thankfully it happened. We got ventromedial prefrontal cortex. We got anterior cingulate cortex that I told you already about these regions earlier. We got precuneus. This area is known to be involved in the interpretation of narrative. So when subjects are trying to interpret a story, this is the area that plays a role in it. So this ISC map looks quite good. But what you want to know is not this. What you want to know is what is different. Does this map look different between those who were indeed persuaded and those who were not persuaded by the health eating call? Right? So in order to do that, we will divide participants into 2 groups. Those who were persuaded and those who were not persuaded. And how we will do it? Since the behavioral effect was in the direction of the sugar-free products, we take the delta of willingness to pay for sugar-free products, correct it for the control condition. We use the median split, and whoever is above is assumed to be persuaded, whoever is below is assumed to not be persuaded. Now, this not persuaded is a very conventional term. If you notice, some participants were mildly persuaded, some were even negatively persuaded, but just for convention, like here, as opposed to the other group, we can call it not persuaded, or those who resisted persuasion. And now we can try to make the same brain map as the previous slide, but now it will be the contrast between these 2 groups. And what we find is that those participants who resisted persuasion actually exhibited higher synchronization of brain activity in these regions. We get VMPFC, anterior cingulate cortex, precuneus, supramarginal gyrus, and rhollatic operculum. VMPFC and ACC I already mentioned from the introduction. So this is already a replication of the previous studies that they are involved. Now about the direction we will discuss later, but their involvement is replicated even with naturalistic data analysis methods like the inter-subject correlation. And we also get the precuneus. The reversed contrast did not reveal any significant areas. So the persuaded group was not more synchronized than the not persuaded in any brain region. Now remember what I told you before, that maybe persuasion is not a matter of local activity. Maybe it's also a matter of how different brain areas are connected. And what we did next was to take these 5 brain regions that were found to play a role in persuasion in this study and see whether they were more strongly connected in one group than in the other group. And what we did was what we call inter-subject functional connectivity analysis. It is basically the same with inter-subject correlation analysis, but instead of just looking at corresponding brain regions, you also look at brain regions that are different between subjects. Yes, and you have this largest matrix basically. It is very similar to functional connectivity for those who are familiar with the term, but this saves you from within subject noise because you look across subjects. So whatever the scanner noise has introduced, you skip it. And what we find is that the non-persuaded group not only exhibited higher reader-subject correlation in these regions, but also these regions were more strongly connected to each other while listening to this health eating call. And with asterisk there, I have indicated whatever was significant, statistically significant in the comparison between the two groups. The last thing, and this is a very good lesson for whoever is like very young scientist, let's say, whenever you have two groups or when you split two groups, you want to make sure always that the effects, I mean, not to make sure, but to limit the possibility that the observed effects are driven by some confound or some covariate that you missed. So what we did was to provide further evidence that the effects are specific to persuasion by comparing this persuaded and not persuaded group in terms of demographics, personality traits, but also fMRI data quality. And we found that there were not significant differences in any of these variables. Yeah, why it is important? As an example, imagine if the persuaded group moved more in the scanner, their heads. This would drive lower reader-subject correlation values, and then we would have the same effects without being, what we study. Of course, this doesn't exclude the possibility, but it limits it. Now, let's move to the conclusions. What we did here was to use a naturalistic persuasive message, a health eating call. We have used it in the past. We knew that it has a behavioral effect. It happened here as well. And we found that VMPFC and anterior cingulate cortex and precuneus especially play a role in persuasion because when we contrasted the persuaded and the non-persuaded group, these brain regions were revealed and actually were more synchronized in the not persuaded group. Okay, more synchronized, or if I frame it differently like in the slide, the persuaded people had less synchronization and more weakly connected brain regions, these particular brain regions. Why could this be the case? Okay, now speculation starts. One idea is that maybe the not persuaded group have perceived the health eating call as misleading. Yes, you remember these studies with the participants with a lesion there, how they were more susceptible to misleading advertisements. So since VMPFC maybe helps us to resist uh, these misleading advertisements, maybe this is what happened here. It is speculation, but it is supported by two evidence. First, that in the contrast analysis, we also found precuneus, who is known to be more responsive when we read a text that we believe is not true, it's inventive, compared to when we believe that it's factual. Okay, so this supports the evidence, the hypothesis. And the anterior cingulate cortex, which also emerged in the contrast, has also been found to be recruited when there is uncertainty about the truth of the text. So when you read a text that you don't know, is it true, is it fake, then ACC is more responsive as opposed to when you know it is true or even when you know that it is false. So it could be the case that the second group had these doubts about the health eating call that they listened. And because of that, perhaps they exhibited more synchronized activity in these regions. Now, although I do remember some of them coming out of the scanner and saying it, this is not a scientific way to put it. And what could be studied in the future is if this experiment is replicated, or maybe even now, if it is not too late, we can consider asking participants to rate after they listen any type of persuasive message. What is your, how much did you believe what you heard? How much do you trust this person that spoke just now? And then use it to better understand the effects. Okay, I regret we didn't do it at the time. Maybe there is still time. We have to discuss it. But actually, we have a follow-up study that we plan now with Nina, who just left, and she plans to compare basically um, the same results, but what if the health eating call was not by an expert, by a nutritionist, but it was like a conversation, casual conversation between peers, like let's say your university classmates, that they discuss about the same arguments and want to see the difference in the effect between this expert persuasion and university classmates, because this also may have some credibility in our perception. So we would still respect Aristotle's principles. And then, yes, in this study, we try to also take these self-report measures. Another direction is to investigate whether the health eating call affected the neural response to the images of the products. Now, if you remember, we just took the segment of the health eating call while listening to it, and we analyzed only the fMRI data corresponding to this period. But what we can also do, we have data to look at the board responses to the images of the products, both before and after the health eating call. And it could be the case that some of these valuation regions that I showed you, like ventral striatum or even VMPFC, might be less responsive after the health eating call in the participants who were persuaded, because maybe in their world, these products does not worth so much any longer. And as I mentioned before, we plan to do this follow-up study with Nina to check whether changing the narrator will change the behavioral effect and perhaps even the neural basis of this resistance to persuasion. With that, I would like to thank all the lab members that helped me in this study, people from the Center of Neurology that helped us collect the data. And I will just leave you with a meme that we had in our poster in Canada. And I would like to invite your questions now.
Okay, some questions. I have a couple of questions. Some questions from the audience. Yeah.
Just clarifying question. I don't really understand the psychological meaning of synchronized activity. You showed this slide. Can you please return to it where there were yellow lines for not for persuaded group, and yes, this one. So these areas are connected in the same way for persuaded and not persuaded, but what's the difference? Thank you.
Okay, thank you for the question. I guess I went a little bit fast in this slide. So what we did, first of all, we took the very same brain regions that were revealed from the contrast. So we used the same 5 brain regions in both groups in this analysis. So of course you will have, the same nodes showing and the same lines. So this is okay. But what differs is the color, and the color indicates, yes, the functional correlation basically. How correlated was the activity in this region with the activity in this region, in this group? Okay, and we see here that all these regions, not only individually were more synchronized in this group, like in the previous analysis, but also they exhibit very similar activity among themselves. But in the persuaded group, it was not the case. They exhibit different responses to the health eating call.
Couple of questions. So one question is more general. Do you think that brain correlates of persuasion can differ for different types of persuasive communications? I mean, your persuasive communication evokes sadness and so on. I can imagine communications that evokes happiness. I can also imagine a very rational communication. I mean, if they persuade you to buy a computer and so on and so on. That's a question number one. I mean, could it be that our results would change depending on the type of communication? The second question is related to the ventromedial prefrontal cortex. I don't know whether many people ask you about this, because that perhaps this most counterintuitive result. Yeah, even you can fit it to the data. I wonder if you can have for example, an alternative explanation. For example, you are persuaded here not by the message, but by peripheral cues, let's say by the expert. And this group simply goes with the expert. So they less concentrate on the message. That's why you see the less engagement. Could it be an alternative explanation? If it could, can or not, can we answer this question in a way? Yeah. So imagine that this group simply follow to the doctors, okay, and don't listen.
Yes, thank you for the questions. I think it makes sense, and we don't have data, unfortunately, to exactly scientifically test this hypothesis, but it could be one interpretation. Um, Actually, I discussed it with Emily Falk, it's like the leading scientist in this field of persuasion, and she had some studies that she found the effect of the VMPFC being opposite, basically, to what we find. And she referred to me this study of connectivity by Cooper that I showed earlier. And when she looked at these pictures, she said that it's not strange because first of all you use different method, and second, which by the way I want to open parenthesis, high the subject correlation might be driven also by synchronized deactivations of a brain region. So this has to be further tested with GLM board traditional analysis, close parenthesis. But she said that VMPFC is particularly involved in persuasion positively when it is connected with other regions. And here we see that it is not connected. Like if you see even these stars do not involve anyhow the VMPFC. So its connectivity with other regions did not differ between the two groups. And perhaps this could be one alternative interpretation, according to her, that VMPFC, we should not interpret it solely by VMPFC, but also based on its connectivity with other regions. It is, yes, I agree that it's counterintuitive. And something that is related to this, but also counterintuitive, is what they are studying now in her lab. They put two subjects in two scanners simultaneously, and they let them communicate freely through microphones and earphones to see what makes an effective, good conversation. And what they found is that diversity correlates with ratings of good conversation. So the more diverse is the experience of the two participants, the better is the conversation and the communication. And they asked actually when are we submitting because they want to cite this research because it relates to that. Yes, we have desynchronization and better communication with the expert. I don't know how much related they are, but it seems to be, yeah, somehow an associated result that they have now, preliminary. Yeah, I think, yeah, the bottom line is that further research needs to be done, and especially the self-reports of trust and all this, I think that they will play a role. Or how much attention did you pay? We could ask like, name how many arguments do you remember from the expert, for example? Yes, there were 13 arguments to see if the two groups differ in this regard.
Yanis, thank you so much. Wonderful talk. Okay, so we make a break for some, and some will go to for workshop. Yeah, so we can join Eliana. I will just remind that we will be back here at around 6 o'clock. Yeah, 10 minutes to 6. We will have a poster session. So we have a break. Those who would like to continue a workshop on morphometry, we have to follow Eliana today.
Yes. So, guys, right now we have some time till our workshop continuation, so we can go for coffee. So follow me.
So some will still join us. Some people are coming, but to keep schedule, since it's a late evening, I suggest to follow our timetable. We have overall 10 minutes for each speaker. Yeah, so the presentation is up to 7 minutes and 3 minutes for questions. I will keep track of the timing. So the first talk is by Valeria on heart rate variability. Let's go.
Okay, hi everyone. I'm very glad to be here at this conference. And today I would like to tell you just a piece of results of my big 2-year project, which is aimed at developing drowsiness detector based on heart rate data. And here is just a small piece of the results that we obtained. And so it is about heart rate variability dynamics from evening to night in individuals with varying levels of daytime sleepiness. So we all know that sleep resistance really requires a lot of body resources and results in body tension. And that's why we made two hypotheses that subjective sleepiness will increase more in people with lower daytime sleepiness from evening till night, and that heart rate metrics will demonstrate some different dynamics from evening till night in people with different daytime sleepiness. And so the objective of this part of the study was to investigate the differences in body functioning among people with different daytime sleepiness levels. To relate daytime sleepiness, we used the Epworth sleepiness scale. Situational sleepiness was assessed by Karolinska and Stanford sleepiness scale, and heart rate data were recorded by polar Ashton sensor. Here you can see the overall design of the study, but for this talk, we need only several parts of it. We need the point where we assess Epworth sleepiness scale about 8 p.m., a bit before it. And also we need scores for Karolinska and Stanford sleepiness scales at 8 p.m. and at 10 p.m. And during all of this experiment, heart rate data was recorded. For this study, I selected 32 participants from our dataset. These were people who went to bed between 10:30 p.m. and 11 p.m. And the criteria also was that their heart rate data was really good. Firstly, we made, of course, data filtering, and then we selected 4-minute heart rate recordings near 8 p.m. and 10 p.m. There we calculated different modality metrics of heart rate, and then we compared groups with different daytime sleepiness. So from our 32 participants, we took only 29, those who demonstrated lower normal daytime sleepiness according to ESS, and those with higher normal daytime sleepiness. Firstly, we proved our first hypothesis that people who have lower normal daytime sleepiness, they show an increase in situational sleepiness from 8 to 10 p.m. and those with more daytime sleepiness, they don't perform such a pattern. If we compare heart rate data between these two groups, we got that for people who are generally less sleepy during the day, their TINN index of heart rate, which is responsible some kind for variability, it decreases from 8 p.m. to 10 p.m. And this can be related to an increase in physical fatigue due to literature data. And for those who have more daytime sleepiness generally, they show a decrease in sympathovagal index from 8 p.m. to 10 p.m., which can indicate that they show less resistance to sleep when they shift from evening to night. Also, we calculated fragmentation metrics of heart rate, which are really new for cognitive and psychophysiology science, but still we calculated them and we got that for those who are more sleepy during the day, generally, fragmentation metrics of heart rate really increase from 8 p.m. to 10 p.m. this is rather hard to interpret, but still we found that, for example, increase in fragmentation of heart rate can be connected to less cognitive performance and maybe to less cognitive tension. So according to the conclusions, we got that situational sleepiness from 8 p.m. to 10 p.m. changed only in people with lower normal daytime sleepiness, and it was accompanied by the TINN decrease, possibly related to fatigue increase. And in people with higher normal daytime sleepiness, the subjective sleepiness scores didn't change at all, but the sympathovagal index decreased and fragmentation heart rate metrics increased from 8 to 10 p.m. And maybe this suggests that the transition from evening to night mode requires a body and cognitive tension decrease. That's all. Thank you for your attention.
Раз. So we have space for questions. Some questions. I have a question. You mentioned that you can explain the difference by physical fatigue. Yeah. Do you have any control for this? Let's say, do you use some questionnaires related to fatigue? This is a current working hypothesis, or what's the status of this interpretation?
About the interpretation, it's just interpretation that comes from the literature. They used shift workers in their study, and they made them work hard or not work hard, and they compared this metric before and after working hard, and they related a decrease in an increase in teen with physical fatigue.
Okay, and perhaps a couple of other questions related to methodology. The first one. What is the age group of your group? Perhaps I missed it. Yeah.
The age group of the whole study is very big, from 18 to 85. But for this study, I collected, I can show you. Here is the distribution. So they were relatively young people. Here we didn't consider age or gender factor because we wanted to find something similar for different people. We only wanted to control the time they went to bed and absence of any chronic diseases and also diseases related to sleep.
Okay, because related question, it's somehow related perhaps to the goal of the study. So do people who are sleepy make some complaints about this state, or they're comfortable with this? And perhaps you can also clarify on the overall goal of the study. I mean, I can imagine that people are happy being sleepy, or perhaps they complain, or there are some problems, or I mean, I can imagine the situation in profession where it's a serious problem. Yeah. Mm-hmm. So first question is, are these people comfortable with this state? And the second one, what is the overall goal of this study?
Okay, thank you. As for the first question about comfort for people, for this group, between these two groups with higher normal and lower normal daytime sleepiness, there was no difference in their replies for the question, are they comfortable with their daytime regime? So we asked them when they generally go to bed, when they generally wake up, and also there was a question, how comfortable you feel about all this. And these two groups, they didn't differ for it. Mm-hmm. And as for the whole study, the goal is to make real-time detector of sleepiness based on heart rate data. So now we are thinking about what metrics of heart rate to include. And this study and some others, we will use them for information what metrics we can use for this model that don't depend, for example, on daytime sleepiness, that don't depend on their sleep comfort mode, about their dreams and so on. So these several studies are used just to make a good model in the final step.
Okay, thank you so much. We're in a tight schedule. Any additional questions? Yes, please.
So in this experiment, we measured heart rate starting at 8 p.m. and finishing at 6 o'clock in the morning. So all the metrics that we calculate, they can be related to heart rate variability. Yes. So I took windows of 4 minutes and I calculated a lot of metrics, statistical ones. I calculated for different bands, low frequency, high frequency, their relation. Also, I calculated nonlinear indices. So overall, no, this were index no. So I just calculated different metrics of heart rate variability. For this study, I used NeuroKit 2 module in Python, and it calculates approximately 100 of different metrics.
Since we're very tight in time, thank you so much. And we move to the next presentation. Okay, Katerina, resting state EEG study. Let's go.
Yes, good evening, dear colleagues. I want to report a part of our results of our project, which is supported by Russian Scientific Foundation. And we are working on it with my colleagues, PhD students, Guzal Khairulina and Dina Michureva, and Olga Martinova, and other colleagues from Institution of Higher Nervous Activity. Um, uh, this project is devoted to investigation of EEG patterns of mental disorders like obsessive compulsive disorder and major depressive disorder. So the mental health issues are some of the biggest concern of our society, and the question about the growth of people who suffered from mental disorders is discussable, but we can see the large amount of people who take antidepressant pills, and the question about how to get objective correlates of mental disorders is very important now. So we performed EEG analysis of resting state EEG data. Here we use a simple resting state paradigm, 30 seconds with eyes closed, 30 seconds with eyes open, repeated alternately. So we have 4 epochs for 1 minute for every condition. And resting state paradigm has the advantages that it needs less effort from people with mental disorders. So it's simple and it makes possible to get the information about the intrinsic neural dynamic, which is at a large extent inheritable and which is very important in the investigation of mental disorders because they have a polygenic nature. And we obtained the data from 34 participants with MDD, 26 participants with OCD, and 43 participants, healthy participants who was the control group. And we obtained um, psychological data with Yale-Brown questionnaire and back depression inventory. And after that, we made an EEG analysis, which involved standard preprocessing steps, connectivity analysis with previous source estimation with Islareta, and we use weighted fuzz lag index to compute connectivity. And after that, we applied statistical analysis by means of ANOVA, which is implemented in the network-based statistic toolbox in MATLAB. And we obtained the difference for 3 groups. You can see it on this graph. It involves 67 connections, and the total amount of connections under consideration was over 80. So 67 was significant, and then we estimated the pairwise differences between groups. And on this graph, you can see the difference, the significant difference between MDD and control group. It has 64 connections. And you can see on this slide that almost all connections were concentrated over occipital regions and also included temporal regions and a few connections for long distance, like frontal occipital connections. And you can see on this slide that the blue ones means the connections was more strong for control group than MDD group, and the red ones was which were stronger for MDD group. And on this slide, you can see the results of pairwise differences. All these results are with Tukey correction. Here we can see the similar pattern, but the amount of connections are less, 48 connections. And also we can see the only few connections which were stronger in OCD group in comparison to the control group. And then we estimated the differences between OCD and MDD group. We found that only 3 connections distinguished these groups, and these connections were stronger in OCD group, and it's interesting that these connections also were stronger for OCD group in comparison to the control group. And if we are talking about the function of these areas, it almost connected with the executive functions, with cognitive control and with cognitive processes which are connected with visual information. And we also estimated the connectedness of the default mode network in free group and get the results that where was the difference between the MDD and control group and OCD and control group, but there was no difference between MDD and OCD group. And also the results with Tukey correction here, it was obtained for alpha and beta frequency bands. Yes, so here are conclusions.
Thank you so much. So we have some space for questions. in Zoom. Yeah, can you make a look? Да-да-да, я понимаю. If you can read in the chat, or you would like to open, Elena, you can just switch on the video and ask the question.
Yeah, this will be better if you switch on the video.
Please.
Yeah, thank you. I have a very quick question regarding your sample. So your title claims that these are patients with mental disorders. So, but it's not clear from your description on the slide. Probably I missed it, whether they were officially diagnosed or you just used this BACS questionnaire and so on to measure this diagnosis in them.
Yes, thank you for your question. I did not said about that because I have a little amount of time. Yes, all the patients had officially approved the diagnosis, and we invited them by our partner clinics. And also we checked the severity of their condition with questionnaires, and some patients were not the patients. They like depressed people became not depressed, and they were excluded from our study.
We also have Diana. Yeah, Diana, feel free to ask the question.
Yes, I have a question. How this data could help to cure patients with MDD?
Thank you for your question.
Thank you for your question.
We don't have the purpose to cure these conditions. We are just trying to find some objective measures, because people with OCD very frequently at the same time have depression. So doctors may have problems to differentiate these disorders, and I think that in the future we need to some more objective measures, not just the clinical interviews.
We have a very tight schedule. We have to stop. Just now I understand your question to Alex Asachi. Yeah, I think it would be interesting to merge two technologies. And also, I mean, what would be interesting also to see like a predictive value, whether you can predict, for example, the severity or the outcome of the treatment by your indexes. That would perhaps additionally verify that it has something to do with the disorder. Yeah? If you can predict the outcome of the treatment or the severity of the disorder. We have to stop here. Thank you very much. Exciting project. We move to the next presentation. Diana, I think, yeah, she's online.
Yes, that's mine, and I need to demonstrate share screen.
Yeah, Diana, you already
have
a right to do this.
No.
Try again.
Okay.
Please try
because
now.
you're now a sole host of the conference.
No, it's still not allowed.
Let me try again.
I have like two accounts, because from one I speak and one I share screen because I have problems with technique.
Ah, okay. So let me try. Yeah, please try now.
Oh, now it's working. Okay. How to? Sorry, 1 minute. Is it seen? Yeah.
It's very clear. Thank you.
Okay. So, dear colleagues, I want to introduce my plan for research. It's my master thesis, non-Euclidean space as potential stimulus for psychophysiological studies, and it's not working. It's not. Oh, okay. Sorry. Andreas Gomez Emerson, mathematician, suggests that during psychedelic experience, the properties of hyperbolic space can be experienced. For example, its infinite number of different types of symmetry, in contrast to limited numbers of symmetries in Euclidean geometry. And for example, feeling that with each step, the branches appears, and the feeling that the space can accommodate more. And fractal geometry is another geometry that we will study, and fractals are another visual object that often seen in psychedelic experience. Also, the AIF is an important feelings that we will include in our research, because AIF is transcendental feeling, and which has been studied before extensively and shown that it could be elicited in participant through virtual reality. And studies show that it's possible that the AIF, it is a reaction to the vast space and the immensity that is caused by a change in geometry. So AIF in general, emotions that include vastness and the need for accommodation. And we suggest that immersing individuals inside virtual spaces provides an optimal method for testing their perception of these environments. The emergence of AIF during VR experience as response to unusual geometry should emphasize transcendental experience. And so that raises questions of brain functional correlates or switching between types of geometries, as well as possibility to simulate a transcendental visual space. And the purpose of the research is to compare brain electrical activity in different geometric spaces using virtual reality as an imitation of the psychedelic experience. And we proposed next, to obtain data on brain activity while perceiving hyperbolic space, in contrast to Euclidean space, obtain data on brain activity while perceiving fractal geometry, versus kaleidoscopic movement. Also conduct behavioral tests before and after the experiment, assess the novelty of the experience, and maybe to compare data that we will obtain and data that already exist in literature. And it will be through VR headset, Oculus Quest, and environments made in Unity, and it will be EEG also during the environments, while environments will be presented to subject. And I guess it will be spectral analysis. And I want to show the examples of VR environments that we already mostly they mostly created. So it's hyperbolic space, and let's look like on this video. We have several colors, but in general, participants will be see this video. And next, I want to show control to this environment. It is a Euclidean space. So control and test environment, they have similar color, and they have similar ways of movement and etc. So they similar of all parameters, excluding geometry. And the next is the fractal environment, and we also have several colors for it. And the control to fractal, it will be kaleidoscopic movement. And that looks like this. In conclusion, this study aims to investigate the electrical activity of the brain during the perception of different geometries, specifically hyperbolic space and fractal geometry, by immersing participants in virtual reality environments with these varying geometries. We hope to simulate aspects of the transcendental experience, which includes psychedelic experience, and elicit feelings of awe, and the potential link between awe and the perception of unusual geometry suggests that geometric patterns may play a significant role in transcendental feelings that associated with this experience. So thank you, and that's all.
Thank you so much. Well, at least I would like to participate in the study. So some questions?
Yes, hello. Thank you very much for your speech. It's a very interesting idea for the experiment, actually. I was wondering how probably I missed this point, how the control conditions were chosen, because I did not really understand why in one control case you had kaleidoscopic visions and in another like square ones. Probably it was in some previous studies. It's just the thing that I'm not in this topic, so probably you can explain why.
Okay, it's like a new idea that that geometric patterns and different geometries could elicit some transcendental feelings. So we, according to like ideas in literature, we decided to test this hypothesis. So we take hyperbolic geometry and honeycomb, that I was showed, and control to hyperbolic geometry, Euclidean geometry, and compare, because Euclidean geometry is geometry where we live, like we perceive like in Euclidean space, not everyone agree, but in general consensus that we see like in Euclidean space. And next, also we have fractal geometry, and and fractal geometry, it's what when object repeat itself several times, and it could be like do it infinitely, and control with kaleidoscopic movement, because it's have the same pictures, but but it's not repeat themselves. It's just moving in another way. And also it was like supported by a professor of math who suggests that control environment to fractal geometry would be kaleidoscopic movement, because they are different, but you can use one picture that moving in different ways. So.
Thank you so much. Other questions?
Okay, thank you so much for your presentation. So what's the practical application of the research findings? Thank you.
Actually, I think that could be that a practical application could be if, for example, we will find connection. Not connection. If we will find that we really can simulate transcendental experience by using VR, it potentially could help some patients in some clinical condition like depression or another mental disorder, because if it is like transformative feeling and it's connected with positive outcomes. So while you experiencing AIF, your life became better. So maybe it could be could be used in medicine, like, or like while it's not major depressive disorder, but like it's a very first stage of depression. I thought about this type of application.
Okay, since we have limited time, I have two small questions. So one, are you planning to produce the stimuli yourself? And the second is, have you pre-tested the stimuli? Do they induce AIF, or you will test it in the future?
Could you repeat the second question? I did not hear.
Have you pre-tested already your stimuli? So do they induce the change status, or you will test it during the project?
So the first question, we have already done almost all scenes, and it was done in Unity. I guess it was your question about how it was made, or
the question was, have you made it yourself? You programmed it?
No. I have colleagues from computer science, game development, and they're they created this scene with my with my commentary, with my idea, and etc. And the second question, we will test it in the future as if it's like induce AIF, we have like questionnaire for this, and
thank you so much. So we have to move on. Thank you. So we have to move to the next presentation. Is it online or offline? Alek, следующая презентация у нас онлайн? Online? Okay, we have online presentation.
It's online, yeah.
Okay, on anger induction. We can see the slides well. Thank you.
But we don't hear anything.
Okay, can you hear me?
Yes, now we can.
Okay, so my name is Vishmi, and I will be presenting about the review that I'm conducting as a part of the contribution to the research by for the research group Vegetative Measures of Valence of Emotional States, which is headed by my supervisor, Vladimir Kostanogov. So just to give you a background of the review plans to provide an overview of the various methods that are used to induce anger in research, and these include external stimuli like films, stress interviews, punishment and harassment, internal such as imagery and recall of past events. So the review highlights several studies that have used different anger induction methods and compares the effectiveness of these methods in eliciting anger and measuring physiological and self-report measures. And overall, I hope that it will provide valuable insights into the methods and challenges of studying anger in a laboratory setting. And hopefully this will help future research in this area. So I'm just going to skip that and just start from this slide. So why should anger be studied? Because number one, it's one of the most common and most powerful emotions that can have significant effects on individuals and society as a whole. And understanding the causes and effects and management of anger can help individuals and communities better cope with the negative consequences of anger, such as aggression, violence, and conflict. Also, anger is a complex emotion that involves cognitive, physiological, and behavioral processes, and studying anger can help researchers better understand these processes and how to interact with each other. Also, third, anger is one of the components of many mental health disorders such as depression, anxiety, and post-traumatic stress disorder. And studying anger can help researchers and clinicians better understand these disorders. So, getting to inducing anger, how exactly can we study anger? Due to time constraints, I'm just going to include two of the most novel ways, I would say, would be through gamification and simulations. So, for example, on the left, you can see a screenshot of one of the gamifications that are being used, which is Cyberball. So this Cyberball task elicits emotional responses in the participants, and it's a computerized ball tossing game where you can manipulate social exclusion and elicit negative emotions such as anger and frustration. And the participants are led to believe that they're playing a ball tossing game, when in reality, they're playing with someone else. But in reality, it's that, it's a computer generated and it's rigged. So eventually the participant will feels social rejection and anger. And the other was one of the studies which used a simulation, and here it's angry driving. So this simulation elicits road rage and anger for drivers, and it can be used to manipulate the participants' emotional state while being on the road and being with other car drivers. And simultaneously, their physiological and behavioral responses can be collected. So the other one is mental imagery. So this elicits emotional responses by asking participants to imagine situations that would elicit anger. So these, and it could be that they are asked to imagine scenarios in which they are frustrated or they're dealing with a difficult person, so on and so forth. Surprisingly, mental imagery was one of the strongest methods to induce, it was one of the most efficient methods to induce anger. So the implications of studying anger is that it helps us better understand the cognitive and neural mechanisms that are underlying. And also it can help us develop effective strategies to reduce anger and for managing anger. So it can also enhance emotional regulation of well-being, and especially since anger is a complex emotion, and it can help us develop interventions which is helpful for people to manage their anger. So some of the challenges of anger induction is that we could have measurement issues, because anger is a multifaceted emotion and it can manifest in different ways, right? Also, usually anger will occur with other negative emotions as well, so it's difficult to just separate and measure pure anger. And also it may not be appropriate for certain populations. Also, there could be issues with sample selection, and there could be other types of ethical considerations. So overall, that's what the review is about. Are there any questions?
Thank you so much. Some questions from the audience. I have a general question. So why do you search for new ways to evoke anger? Are you not satisfied with the standard ways to do it, or there is no still standard methods? In general, what is the goal of your review? Can you hear us? Vishimi?
Okay, so if there are no questions, I'm going to stop sharing.
Can you hear us? Vishmi? It's a good way to run away from the answering the questions.
Vishnu, can you hear us or not?
Or are there any questions? I'm still here.
Can you hear us?
There are questions. Please, are there actually questions or not? Or can I move on?
Ras. Can you hear us?
Okay, I will let Alfred present.
Okay, guys. Due to technical reasons, we move to the next presentation, and the next presentation by Alfred. Yeah, is it online or offline? Online. Okay. Hope it will work better. Okay. Also, body temperature as a markers of basic emotions. Alfred, are you with us?
Yes.
Perfect.
Yep. Let me share my screen. Can you see my screen?
So we can. You can also use the presentation mode. We see your slides right now. Perfect.
Good.
We see everything.
Okay. So I'm Alfred, and I'm presenting on body temperature as possible marker of basic emotions. So emotions as a concept has been studied severally, most especially in the lab. However, they focus most on facial muscles without considering other distal parts of the body. But with current improvements in technology, we could also gather or measure temperature or emotions elicited from other parts of the body. So based on this, that we hypothesized from this study that temperature and muscle changes or activities would change depending on emotions elicited. So how did we elicit the emotions? We took 35 pictures from International Affective Picture System to elicit some basic emotions, including fear, disgust, joy, sadness, surprise, and anger, as well as other neutral images that did not induce any emotions. So the pictures were shown in a 12 seconds interval, and each set was generated randomly for each participant. And each set was followed by basic questions using Likert scale. So after showing the picture 5 in a row for 12 seconds for each participant, there will be a Likert scale system where the participant would have to use the mouse to click or rate how he or she felt after watching the images. And then we used electrodermal activity, cardiography, and electromyography, as well as temperature sensors to check for these changes in muscle activities. The sensors were placed in 4 different parts of the body, including the temple, the larynx, which is the throat, the solar system, which is the stomach, and then the trapezius, the upper part of the shoulder. So this is how the participant looked after putting on the sensors. In all, we had 34 participants, but because of some data collection errors, we had to drop 2 of the data collected, so we had 32. So to measure the temperature, we averaged obtained values for each of the image blocks. So we set the first 10 seconds as a baseline for measuring or checking the changes in the temperature. So for electrocardiography processing, we use Neurokit to Python program to extract heart rate, HRV, and then mean. But this was not mainly the focus of this aspect of the project. So this is the behavioral responses for the emotions that were elicited and the using the different stimuli or pictures. So in all, the answers of the subjects really differed. They were different, like very, very different from each other. And then when we measured the pictures, the set of fear pictures scored very high for the anger scale, but it was not significant. Again, the set of pictures of surprise also scored really high. So we move on to the psychological responses. As shown in the picture, the red parts are the most significant parts. So from the table, you can see that sadness positively correlated with the sensors that were placed on the trapezius. So it means that the sadness could contribute to changes or temperature changes in the trapezius muscle. In the same way, sadness negatively correlated with the sensors that were placed on the solar plexus, which is the stomach. So it means that when sadness is induced, there will be changes in temperature regarding the stomach activities. When we come down here, you could also see surprise also having a positive correlation with tempo or changes in the tempo muscles. And then we try to check for correlations between the different temperatures, and some are significant, some are not significant. This is the correlation between sadness and trapezius, as already discussed in the table. It has a positive influence. So this is, and this is the correlation between solar plexus and sadness. It is a negative or inverse relationship. So in conclusion, first, the analysis was based on only temperatures, so we didn't, as I said earlier on, we didn't consider heart rate variability and all those things, which will be done later. And then again, the sample size we think is too small, and then the study can be replicated with a very big or bigger sample. From the table, we can see that in general, sadness seems to make a very significant correlation with temperature changes in comparison to the other emotions. So further experiments and investigations can be done, because this is just correlation. It doesn't mean this is cause, or it doesn't show causality. So other experiments or projects can be done. So, that is it. And thank you. Waiting for questions.
Okay, thank you so much. Some of the questions, yeah. I also have a couple of questions.
Thank you, Alfred. So you mentioned that sadness would induce temperature change. So I wanted to be specific. Is it lower in temperature or higher? Does it mean that if I'm sad now, my stomach will be colder or a bit, hotter? Please, can you make us clear on this aspect? Thank you.
Okay, so the correlation is inverse, which means that the higher your sadness, the colder your temperature could be, or the lower your sadness, the higher your stomach temperature could be. So it is inverse. So that is what it means. I hope is your question answered, please?
Thank you so much. We have also a couple of clarification questions. Can you remind us what was the time window for the analysis of the temperature?
10 seconds. We
10
use
seconds.
10 seconds as baseline. Yes.
Just wonder, can it affect your results if you will analyze longer time windows or shorter time windows? Or you base your analysis on the literature?
I think it was based on literature, based on the review that we did. Most papers use 10 seconds as baseline. That's why we adopted the.
Okay, and a bit related question. So our colleagues in Finland, they made some whole body temperature analysis, classified emotions. I think they they focused on patterns. Do you plan to focus on single areas in the body, but it can be that a configuration of temperature in different areas, like patterns, would be more predictive than a single area?
And so we like I said, we measured from okay, thank you for the question. We measured for 4 different parts of the body at the same time, but the results show that some parts of the body did not show any correlation. So we didn't measure them separately, like one after the other. We put the sensors at the same time, start the experiment at the same time, measure everything at the same time. But the analysis showed that some parts of the body did not elicit any changes, did not show any changes.
So we are well in time. Thank you so much, Alfred. Good luck with your project. Thank you very much. Very interesting. And we move to the last presentation. It's still online. Elena, yeah. It's scary, yeah. So yeah, I see that artificial intelligence can see you. I mean, the title is scary.
Can you hear me?
Can see you. Okay, I think your slides also, yeah, very well seen. Thank you.
And what about the sound?
Sound is perfect.
Okay, thank you. Thank you for the audience for surviving till the end of the conference almost, I mean today. So I'm presenting our work that we conducted like a year ago or a bit more, but still hoping to publish it one day. So this is a project on attempt to extract personality traits from gazing behavior in natural environments. You can see here a team of researchers working on this project. We also have here people who work on this automatic recognition part and people who are working on ideas. So background of this project looks like this. So if you take a look at how personality traits are recognized from different gaze behaviors or gaze features, you can see two sides. First is laboratory studies, which use many algorithms, many traits, but procedure is usually more or less the same. So participants sit in front of a computer and view some kind of stimuli, usually emotionally or socially loaded pictures or videos. And after that, when they process these gaze behaviors extracted from my tracker using these machine learning algorithms, they receive a huge accuracy, like up to 95% accuracy. On the other side, you have natural setting studies. We have like probably only a couple of those. And we are basing our research on this study by Hoppe et al. From 2018. So in this case, you have usually a small amount of ML algorithms applied. You have restricted amount of big, of traits, for example, big five and curiosity. And in these studies, they allow participants to stray on the street or go to some specific places like a shop, and they track their eyes during these walks. And in these studies, they receive quite low accuracy, like up to 40 or 50% at maximum. So in our work, we aim to extend this natural setting study by applying more ML algorithms and collecting more information on traits, like adding more traits to the analysis. So in our case, we collected quite a small sample, I agree, but it's more or less okay for a tracking study. We used Tobii glasses for collecting data on gazing behavior. So our participants first finished personality questionnaires. We used Russian translations of Big Five inventory and short guide triad questionnaire. And then we allowed them to go to a museum within one building. So they were first entered the lab where they filled in questionnaires. Then we applied this eye tracker to them, and they went to this museum. So we tracked their eyes while they were walking to the museum around 2.5 minutes. Then they were in the museum with the free viewing task for 10 minutes, and they also tracked their eyes while they were going back to the lab. Again, 2.5 minutes. So these are kind of two different conditions for the participants. We extracted around 200 traits, gaze features from these gaze recordings, and we applied 8 machine learning algorithms. All of those were used in previous research except perceptron, which we decided to add to see whether it works better or worse in comparison to previously one used. Here you can see briefly the results. These are results for the whole recording. So these 2.5 minutes before and after the museum, and 10 minutes within the museum condition. The results are not really impressive. You can see this theoretical chance level line. It's for this particular study, it's 0.3, 33. If well, I'm going deeper into this, but this is a random line, like random chance prediction, and you can see not really impressive results here. But if you go to other parts of the recording, so from the way part of the recording, you can predict a bit better. And finally, museum part again shows not really impressive results. So you can see that the prediction is around 0.4, which you can see in previous studies. So what we can conclude from this is that extracted eye movements introduced to machine learning algorithms actually can work to some extent. It can predict personality traits. Not all of them, but at least extroversion and Machiavellism with an accuracy of like 0.3, 0.4, 0.5 in some extreme cases. And it is comparable, our results are quite comparable to previous ecologically valid studies, but it's much lower than laboratory-based research, which shows accuracy of 0.9, which can be a result of machine learning algorithms working in this way or just a condition. We also can see that some traits are not really predictable from this data, but probably it's just the case of the task, because we use free viewing task and participants just had no chance to express their conscientiousness, for example. So these differences in predictability might just stem from different trait activation during the task in this environment. We also think that different algorithms might be applied to different parts of the recording because they seem to capture specific gaze patterns, for example, the case. And this might help us in future to predict traits a bit better from this ecologically valid data. So we are hoping that at some point we might be able to create an assessment method which is much better than just questionnaires. We can extract personality traits from behavior. That's probably it. I'm ready for questions and collaboration on this and other projects. Thank you.
Thank you so much.
Thank you, Alina, for an interesting report. I have a question. I'm sorry if I missed it. Why you chose the museum for the place? As I think that there is a place which is more connected with narcissism, Machiavellism, and other so-called negative features.
Yeah, it's a good question. Thank you. So we didn't have any particular hypothesis regarding expression of traits within this environment. We wanted to enter our participants in some environment where they may spend 10 minutes not so boring to, 10 minutes sitting in a classroom, for example, or doing something really boring is not really pleasant for participants. It might be hard for them to participate in such studies. So museum was just an entertaining place where they can spend 10 minutes with the free viewing task. So they didn't have any task. It is just kind of it was a good decision because we didn't have any particular hypothesis from previous research how it might work.
Okay, because I also had the same question. I mean, why not to provoke people differently for indicative behavior? Yeah, so museum is a great place, but I don't know. Perhaps extroversion, introversion can be expressed much more specifically in other settings. Yeah, but at the same, I got your answer.
Yeah, so probably in future studies, it might be a good idea to place participants in different environments, like new environments, boring environments, environments where they need to express their consciousness, like where they perform some kind of task and they feel this pressure to perform a task. And then probably we will see this trait activation. Yeah.
Elena, thank you very much for your talk. I also have a question concerning features and metrics. You pointed out that you had plenty of them, and my question is whether they make any sense or they were just automatically feature extracted.
Yeah, thank you. This is a great question. So about the traits extraction procedure, we used Python code openly available from previous research that we were basing our study on. You can see this link to Hope et al. So this is our colleague who shared code, and you can find it yourself in this publication. So we adapted it to our eye tracker, and these traits have sense. I mean, they are pupil size, saccades, engrams of moving eyes from different there were metrics and engrams of moving eyes from one point in this matrix to another. I'm not sure at the time explaining it clear, but this is not just traits that or features that ML algorithm just invents. They make sense actually.
Okay, thank you very much.
We also attempted to do this feature importance analysis, but it is not available for all of these algorithms. Some algorithms do not have this feature, and it was actually more or less meaningless. We couldn't interpret this, unfortunately.
Okay, other questions? I have a question, perhaps because one team in the Department of Psychology, I don't remember the quality, but they classified extroversion and introversion based on faces of the participants. I mean, I just wonder, would the photo of your participants would add something to your results?
Yeah, probably. We didn't try this. Maybe yes. I'm not sure that it might work. It sounds a bit. Yeah, probably.
There is actually, because I also browse the literature, there is a large research on this topic, and I was surprised by the paper first, but I found some papers that more or less fit Big Five to facial patterns. Yeah, I mean, it's just a crazy suggestion that you could collect.
Yeah, that's fun. We might try this. I think it might be more or less predictable from moving faces, like dynamic one, when people express their emotions or something on their face. So in this case, might be quite good accuracy. But static photo, it's impressive.
Thank you so much. We finished well in time. Thank you for your talk. Thank you everybody for your attention to our poster session. If you have time, I hope to see you tomorrow at 11. Nina Kazanina will give a talk. She is now in University of Bristol. Yeah? And also, if you would like to spend some time with regression, we will have a workshop on regression analysis at 3 o'clock. So feel free to join Ksenia Panidi and learn the recent developments of regression analysis. And if you will need a lab tour, we will organize a lab tour at 5 o'clock. So let us know during the lunch break tomorrow that you would like to visit our conference, our lab. Thank you so much. See you tomorrow. Bye.
Recording stop.